Hello，有听到吗
听得到。
？OK，谢谢。
可以了哈。
可以。有看到画面吗？
也看得到。
简报的部分有吗？有看到简报档吗？
简报没有诶。
现在呢
现在有了，现在有了。
？OK，
讲话啊，
滑鼠到时候就是下一张这样。
好，
按键盘，
按键盘。
键盘。
现在有听到声音吗？
有听到声音？
有
听到声音哦。OK，好，那等一下我们就按照这个声音还有画面来进行这个课程。我们就4点钟开始。好。想知道他们有多少人？不知道。
刚刚看了一下有18个，那应该还会再录。所以要加入这个 Google Meet 才会好看到的。
对。他那个Cisco也在做。
哦。
他们建议我们，那个台北的课程这样出去。那等一下那个门就稍微开一点点。
可以。抱歉。
还有2分钟。 我们准备开始了哈。那这样可以吗？我要开始了，可以吗？
好，可以，这时候你可以先开始了，4点了。
好。那我们今天第一场这个量子电脑的挑战愿景，我们大概讲的就是基本原理，还有重要演算法。那再来是讲它碰到的困难，最后就是说那些基础原理，就物理的这个基础原理会受到量子电脑的发展，会受到什么样的冲击？啊，再来就是量子电脑未来发展的愿景。那这张图是在讲人类的脑神经，还有现在半导体元件的工作的一个物理面图啊。那我们在看到量子电脑出来之后，所用的是直接是量子力学波函数的这个演化方程啊。那它的反应的速度就比目前的电脑的速度要快到1000倍左右，平均1000倍到这个或者是10^6次方倍哈。那原因就是因为它所用到的这个波函数的可能是电子的质显或者原子核的质显，这个特征时间都很快。所以未来量子电脑的发展呢，当然对传统这个电子电动的传输的这个系统会产生很大的这个颠覆性，但是它碰到的困难也蛮多的。我们要理解现在传统电脑，它的基本是在40年代、50年代，Neumann提出了让记忆体跟计算元件跟控制元件分开的一个电脑架构。那么量子电脑呢，没有这样的类似的架构，它的记忆体、它的控制跟它的这一个逻辑运算是结合在一起，这也是它目前的困扰。我们现在看全世界传统电脑，就以超级电脑为范例来看，就知道说每一个地区它的科技的水准跟竞争。我们看全世界超级电脑大概每一年有2次做一个评估，哪一个地区哪一部的电脑，它的计算力是多大，排名是多少？那现在以区域来讲，欧盟是最多哈，计算力跟这一个超级电脑的这个步数是排第一，计算力是第一。那美国是计算力排第二，日本是排第三。那中国大陆它虽然超级电脑的数量很多，可是总计算力算排第4。也就是因为中国的超级电脑呢，让美国觉得中国是一个潜在的竞争对手，在这个数量上就可以看到。那么我们台湾有3部的超级电脑是排进前500名，但是还输韩国也是3部，但是名次比台湾多一点点。但是我们注意看，全世界前500名啊，在欧盟、美国、日本跟中国这3个地区加起来就486部了，只剩下10几部是其他国家在分，所以这个也可以看出一个国家的这个科技的水准。那么古典电脑跟量子电脑最大的差异就是，如果我们以矩阵的角度来看，古典电脑如果是 n 个位元，那它的计算它的运算法呢，就是 n 平方的矩阵。那量子电脑如果有 k 位元，它呢，产生的量子位元数就是 O 的 k 次方，就造成了量子电脑的这一个演算法，它就 O 的 k 次方乘 O 的 k 次方，所以它是一个很大的一个矩阵的一个运算。那么 O 的 k 次方什么时候会大于 n？ 就是我们在看量子电脑什么时候会取代传统电脑，但是事情也不能只是这样看，只是说数量上来看，大概就是 k 到500到1000的时候呢，已经让这个计算量非常的大。好，那么量子电脑它能够 运算的一个基本的特色，就是利用量子纠缠态啊。等一下我们再会讲这个纠缠态的特征。这个纠缠态本身呢，可以在两位元的计算的时候呢，会把一个位元跟某一个位元的特殊的状态结合，然后在一个 O 的 n 次方的 space， 我们刚刚是用 O 的 k 次方来讲，那这个地方如果我们有 n 个位元，它就 O 的 n 这个次方的可能。这个 O 是从哪里来？这个 O 就是每一个位元都有0跟1同时存在的状态，所以它一直在那边跳来，一下子跳0，一下子跳1。那么第二个位元也是一下子跳0，一个跳1，所以它每一个位元就有2个可能。那 n 个位元就 O 的 n 次方的 space。那下面这个是在一个符号的计算上，就是把第一个位元的这一个0和第二个位元的1，第一个位元的1和第二个位元的0纠缠起来。那除了这个 O 的 n 个 space 的激励空间之外呢，另外就是纠缠。我们右边看到的这个图，就是0跟1，1跟0的这个纠缠，就是只要上面是跑到1，下面一定跑到0；只要是上面跑到0，下面一定跑到1，这就是一个纠缠的现象。那么因为有这一个纠缠的现象呢，使得物理学也受到冲击。也就是说，这个纠缠的相互作用会跟狭义相对论的所谓在类空领域里面没有办法相互影响的事件产生相互作用。那么物理学到目前为止还没有办法完整去解释这个纠缠态它的内涵是什么。那么可是计算科学已经把它纳到整个量子电脑的计算模型里面。在看到量子电脑在运算的过程当中呢，希望把一个位元，我们刚刚讲的一个位元，用一个数学的公式去表达它。那因为量子态它的系数是一个负数，所以呢，它可能制造出来的就可能用一个球面外加一个单位元的所谓直积来表达。那这个球面上呢的北极就是0，南极就是1，这是一个数学上的表达公式啊。如果各位有兴趣，很多量子电脑的书都有写。那透过这种方式来操作量子电脑单位元的运作。那这个运作呢，我们如果以图灵机，所谓图灵机就是最原始的电脑的概念。我们看这个一个传统的图灵机在1这个地方呢，它每一次只能够移动一个位置。如果我们是激励的图灵机呢，我们就说它一次可能在这个地方有4个可能，不过它可能是有这个0.1的几率是在第一个地方，0.5的几率是在另外一个地方。那你要看那个几率的选择到哪里，它一次只要按照那个几率决定去跑，那它的机会就比传统电脑的几率就高一些。那量子图灵机呢，就是最右边这张图呢，它事实上，我们看到，如果它是在第二个位元产生作用的时候呢，那些线就是它对别的位元的影响。如果我们一次是2个位元产生作用的时候呢，它的线又增加了。如果我们是3个位元同时做的话呢，那所有的位元对所有位元都有影响，那个线的数目又增加1倍。所以整个量子的图灵机本身就已经隐含着它的计算的这个可能会比传统电脑还要来得快，因为它是平行的在运作。那么从数学的角度来看，那么如果各位不是理工背景的，就只要粗粗的认知说，在量子电脑我们要为它去设计一个演算法的基本单位呢，我们都是用矩阵来反映。而这个矩阵的特征值呢，在量子电脑的这个领域的人呢，都知道它是单位元上的复数根，也就是说，我们就是用腰正矩阵来研究量子电脑的逻辑差。那它的特征就是 它的每个标正矩阵的特征值呢，都是单位元上的位置的这个平方根所得到的啊。比如说你可以想象说，每一个演算法里面的那个逻辑差，它的特征的值都是在单位元的这个复数平面的单位元上的这个一的这个均方根哈。好，那么它和古典电脑最大的差异在哪里？量子电脑所用的是可逆的逻辑差，古典电脑，台积电今天所生产的所有的晶片都是不可逆的逻辑差。不可逆的逻辑差，它是2个输入1个输出；可逆逻辑差呢，它是2个输入2个输出，它可以用结果去推原因，可是传统的逻辑差呢不可以。那么大概1980年代有一些人呢，就去研究古典的可逆逻辑差。那么古典的可逆逻辑差呢，在所谓通用逻辑差的这个发展上，我们在讲通用逻辑差的角色，就是说，如同我们这里的朗 end 是古典的逻辑差，它可以当成通用逻辑差，就是它可以用朗 end 呢来组成古典电路里面所有的电路，所以它叫做通用逻辑差。可是它是不可逆的通用逻辑差。那么可逆的通用逻辑差，可逆的通用逻辑差至少要3个位元，这个大概是在1980年左右提出来的。那我们用同样的角度来看量子电脑的通用逻辑差的演化的历史。量子通用逻辑差是3个位元，3个 qubit 是在1989年由大许提出来的。就是说，如果是量子运算用的逻辑差呢，是大许他去写古典的3个 bit 的通用逻辑差放在量子电脑，1989年。到了1995年呢，这个 Barenko 呢，他同时在这一年发表了，有问题吗？没有，我就继续讲了哈。在1995年呢，他发了2篇论文。第一篇论文就是说，量子通用逻辑差的可逆通用逻辑差呢，只要2个位元就可以。那是95年。同时在那一年，他也发表了说，这一个2位元的通用逻辑差很难运作，所以他就把它画到那个我们刚才布洛赫图上面的，它有4个 1 qubit 的逻辑差，就是只对1个 qubit 的作用，就是 OX、OY、OZ， 还有一个相角 phi。那另外呢 ，2 qubit 的逻辑差呢，就是只有一个 control node、G node， 这是在1995年。到了1997年呢，有人就把我们放在讲义上面的这一个第2层次的通用逻辑差，又用 Hadamard gate、S gate、T gate 跟 C not 不动啊，它来可以逼近，他说它可以逼近通用逻辑差做到的动作，所以现在很多人就把2跟3，我列在这里面，2跟3的东西的混合来表现逻辑差在量子电脑里面的运作。但是最后这一个简化版本呢，它是有一些误差在的。好，那么通用逻辑差长得什么样子？我们看左边有看到 h、x、y、z， 每一个逻辑差都对应着2乘2的矩阵，就是单位元，就是2乘2的矩阵。好，那么也看到了相角 phi、OX、OZ、OY 的矩阵的表示，这也是单位元的逻辑差。那双位元的逻辑差呢，就我们看到的，就是 control not， 就是 C not， 在第2个最右边的第2个就是 control not， 它就是把一个位元，如果上面经过的是0，它就不动啊；如果上面那个黑点通过的是1，下面就要改变它的状态，它就是一个 C not。详细的话，当然你要看书了哈。那量子电脑怎么工作呢？我们现在是在一个理想状态下看量子电脑怎么运作。在理想状态下呢，就是你要输入 你的式子，然后你要做初态的备置，一般都是把初态定为0的方式来输入。但不要以为量子电脑做0是很容易的，因为在量子态呢，你要把一个状态定在一个固定的状态是很困难的，所以初态的备置已经很困难了。然后呢，再由我们刚才讲过的量子演算法的那个通用逻辑差构成的一个标正，我们这里所谓标正操作，就是刚才因为每一个量子的通用逻辑差组成的就是一个标正的矩阵，所以它有一系列的标正矩阵在相互作用。那么对于做演算法的人呢，他就必须要有从目标，就是你的目标要做什么，那你要去找到适当的演算法。那量子演算法呢，到目前我们看的就是说被认为是真正量子演算法，一个就是达西·鸠萨是在1992年提出来。那他提出来的时候呢，让某一种判定的函数呢，可以比传统电脑要快，所以这个只是一个演算法而已。那秀演算法呢，是1994年提出来的。我们大家在听的时候呢，特别要注意这个年代，因为这个是等于量子电脑发展的一个阶段性的东西。那么秀演算法提出来的时候呢，才让量子电脑的这一个威力让传统电脑感到恐惧，就是说它可以解现在的密码学 OSA 的密码学。那到了1996年呢，才有 Borel 的演算法提出来，这个是它的搜寻的这个次式呢，传统如果一个结构化的数据要有 n 次的搜寻，它只要有根号 n 的方式去搜寻就可以得到。基本上我们在量子电脑的学习上面没有学习这3个演算法，等于你没有学到量子电脑的入门了哈，所以应该从这个演算法开始去学习。那演算法有了之后呢，它要化成通用逻辑差的编程，因为如果你不用，你有演算法不会弄成通用逻辑差，量子电脑的硬体是看不懂你叫它做什么事，所以一个很大的困难是演算法怎么变成量子通用逻辑差，这是一个很大的挑战。好，那我们看到量子电脑它遇到的挑战是什么？第一个，这个演算法要用通用逻辑差来表达，已经很困难。等到这个演算法要真正成为一个实际的解决人类工程问题的，那又是一个很大的难题。这个难题在哪里？第一个就是它的噪音问题，也就是说，如果你把量子电脑的元件放在常温之下，那根本无法操作，因为热噪音已经让量子的这个它所谓的这个相干态呢会破坏掉。那么如果你是要把它放在很低的温度里面呢，那你要付出的能源代价是很高的。所以它的困难来自于，第一个是低温的问题，第二个纵使在很低的温度，将近绝对0度的话，它还是有量子噪音。如果温度高一点，就是有热噪音。那在运算的过程当中，你如何确定你做的动作是对的？这是一个很大的挑战。所以理想上它是可以去取代传统电脑，可是实作上是很困难，而且它的演算法的概念跟传统演算法概念是完全不一样。那我们刚刚也提到了，量子电脑呢，它没有储存器，所以在控制量子电脑的那些电路跟输入我们已经知道的数据要到量子电脑去做，都需要传统电脑来帮忙。所以也就是说，以量子电脑那么大的计算量你没有超级电脑是不可能。所以我在前面就特别提到说，各个区域超级电脑的分布，让你可以了解量子电脑可能会成功在哪里。好，这是它面临的挑战。那么面临挑战呢，它用到的是固态物理、拟态物理、介观物理、量子场论等等。我们等一下会稍微再提一下。好，这个就是我们看的低温。 所以量子电脑的做到绝对零度附近的时候呢，都已经要用液态氦来做冷却。所以我们这里列出了不同物质的它的这个沸点的温度，然后所以你大概它可以冷却的就是它的下限啊。那现在要用液态4跟氦4啊，还有氦3操作温度更低，所以你要操作在现在你看到的 Google、Amazon 或者是 IBM 他们都用冷却的这个要氦3的这个液态的情形来做冷却啊。那这是它低温的挑战啊。现在冷冻机不便宜，一整套的冷冻机就要5000万台币左右。那一个做量子电脑的单位，可能一次要买4部来轮流操作才可能，所以还是很贵的硬体设施的低温的挑战。第二个是我们讲到最后一个挑战，刚刚讲过的噪音，刚刚讲过的低温的设备，现在来谈就是说它的这个位元跟位元之间啊，它必须做资料交换。如果它是前段接，也就是说，像左边这张图，那么它从1、2、3、4、5，从0、1、2、3、4、5这6个节点，它的前串接，它如果要跟隔壁做2位元的操作呢，它直接就做就好。可是现在我们已看到公告，可以看到可以在台大的这个计划案里面看到的 IBM Q65 65个 qubit， 它的拓扑就长这个样子。所以当我有一个0标号是0的位置的，要跟64这个位元做资料交换，它走的步数可能就要30步，也就是它的 2 qubit 的这个 swap 做交换的动作要做30次以上，而且他在做交换的时候，他还确定别人没有在做别的工作。所以如果这个拓扑的问题不解决，那量子电脑未来的路就很坎坷了，也就是它被局限在很小的系统上面。好，我们讲到刚刚讲的这一个密码学里面提到秀演算法，大西鸠萨就比较我们不讲。秀演算法它就是为了解破 OSA 的密码。那 OSA 的密码呢，它是透过去解一个很大的这个合成数来创造公钥匙跟私钥匙，所以你只要有公钥匙，你就可以有私钥匙。那么我们在看这个过程里面呢，那么假定 Bob 有一个铭文，他要透过一个公钥匙来加密的时候变成密文，再给 Alice 呢，他已经自己生产的这个私钥匙呢，他就可以来做一个解密的过程。所以我们今天看到的这个 N 跟 E 啊，是公共的钥匙，也就是说你可以很容易去拿得到的，大家都可以拿得到的东西。拿到这个公钥匙呢，他要去破解这个 N 是 P 跟 Q 组成的，很困难。那量子演算法呢，就是为了这个地方提出一个新的演算法啊。那这新的演算法是怎么做的呢？也就是说，如果要找一个合成数，那它也是用找最大公因数的方式去解这一个大的 N 是 PQ 所组成的。它要看这个我们猜的一个值是不是和 N 有公因数，有公因数就是可以找到 P 跟 Q。那它这个解法是很特征的，很特殊的。它去找任意数小于 n， 然后呢，它去找 ax 去 mod n。很简单的想法，你就是 ax 的次方去 mod n， 它的周期是多少？这是一个很奇怪的想法啊。它有了周期偶之后呢，它就可以借着这个周期是偶数的情况之下呢，来把这个密码解出来。所以它就可以走到把这个合成数的密码 P 跟 Q 把它解出来，它就可以解到私钥匙。那我们来看一个很简单的例子，这是我的讲义里面，我上个课的讲义里面的一个例子。就假定我们现在的合成数是15，你手带了 A 是7， 那么我们就把7的0次方、1次方、2次方、3次方、4次方一直往前算。我们在这个算的过程当中，就发现它的除下来的这个余数呢是17413，17413。在这个例子里面呢，我们就看到它的这个余数呢是周期是4。那你如果知道它周期是4，你在 a 等于7，你就可以分解到15这一个合成数。这个我们就不太多讲，这是秀演算法的方法啊。那么，所以秀演算法呢，它在解这个质因式的过程当中，它只是在解这个质因式的一小段，我列在这个图上，在那一小段的地方来解决。其他的还是要古典电脑来帮忙。好，那这一张图的这个左上角，我们看到，如果我们有一个数，它是937乘947，它就是一个很大的数目，你要乘法很简单。可是我们有一个数呢，887339变成 P 乘 Q， 你要解就很难解。这个就是说，大的合成数作为密码学的原因，就是你要去解得到它的质因式是很困难的。比如说，我们现在1024个 bit， 现在放在数目上的这个数目就是16进位的1024个 bit 的数目。那你如果是传统电脑来做一个这么大的位元数的密码，要你去分解的话，传统电脑要300年。那这个图上呢，有秀的最下面的那个蓝色这条曲线呢，是秀演算法的理想模型，就是秀到外面去演讲，他就在讲这一条线。那这一条线呢，跟排在第3条线的这个就是红色这一条呢，就是古典电脑要解的时间。可是秀演算法呢，他提出来之后，他并没有把它化成通用逻辑差，所以秀演算法如何作为通用逻辑差这件事情是很大的挑战。那么我的实验室已经做出了，就是说，如果你硬要把，因为秀演算法当中会用到量子傅立叶转换来当一个加减法的平台，加减剂是用傅立叶转换来做的。我们做了一个初估我们最上面那一条线就是几乎发散那一条线，就是量子电脑的这个通用逻辑差，全部用量子演算法，用这个傅立叶转换来做加法、减法、乘法、除法。那它的位元数是很可怕的它要解的时间比古典电脑还要麻烦，对，发散那条线。那我们实验室呢，还做一个，就是说，如果我们跟古典电脑结合，有一半的电路是量子电脑，一半的电路是量子电脑的话呢，那我们可以得到比较，这个声音也怪怪的。我们可以算出一个50分钟可以算出来，但是它位元数要52万个。目前还在改善当中这是我们这一届的硕士生在做。这个有没有人有问题呢？
请线上的学员能够把那个声音关掉吗？让教授可以继续他的演讲。
好，那这里就是讲 Global 演算法，用很简单的图。Global 演算法就是说，它第一次先把所有的你要去搜寻的对象，如果你知道它是在哪一个地方被你编码了那么它第一个动作就是把那个编码的相位倒转了180度，就大家都是向上的时候呢，它有一个是负的。那第二次动作呢，大家又回复到相位的时候呢，它会把其他的不是你搜寻的对象的这个振幅呢压低。 那么把你要找的这个正弧提升，这是勾本演算法。那么我这一次在台北办的这个讲座呢，就特别讲勾本演算法跟 AI 结合的课题。那当然它的演算法就是这么简单的图示，可是实际上你要去操作，还是很多通用逻辑差的问题要解决。好，那么现在发展到哪里？因为量子电脑所答应的、所做的梦想呢，是可以取代传统电脑。可是呢，因为有噪音问题，有这个低温问题还有它网络拓扑的问题，所以它一直没有办法去回应说它跟传统电脑比赛的能耐。所以现在呢，就差不多从2010年开始，就一大批人开始去做一个它容许噪音，而且在短期间可以看到的这个量子电脑可以做的东西。他们讲的叫做变分量子演算法。那这个是在我台北这次课程里面有专门谈到这一块。那也就是说，它的 qubit 不要太多，比如说 qubit 只用4个或5个，然后量子电脑的演算的这个步骤不要太长。你的步骤太长的话呢，你现在量子电脑就每做一个步骤，它的误差就会增加。所以现在等于是你还是用量子电脑，但是呢，有一半是用传统电脑，两者去互相帮忙，来把这一个某些最佳化的问题，或者是 AI 的问题来做解决。这个就是现在在做的东西，目前最热门的课题啊。那另外一个就是说，它不用我们那种通用逻辑差，它只用一个简单的，我们刚才看的那个逻辑差，它只用一个简单的 z 那个作用，01，它只选择那个作用，它没有其他的相角的问题。那么就是所谓的量子退火模拟法。那么这个东西呢，有一个公司叫低位，那么它已经成立了，加拿大的公司成立很久。那目前他们认为他们可以做的跟 VQA 很接近，大概是下面这几个领域，有包括这一个治安的，有包括人工智慧的，有包括金融模拟的，有包括这一个气象预报的，或者药物设计，像这一次的这一个COVID-19 的这个问题还有这个量子化学的计算。那几乎你可以看到在变分量子演算法所能做的，在模拟退火法呢，都差不多有都可以做的方法，因为两者都是从最佳化的角度来做切入点，所以这个是目前最热门，而且是我们可以 touch 它。但是我们可以 touch 它，不代表说它已经有商业的价值这个它还是有段距离。简单的说来讲，目前我们所看到的，这是我这次在台北开课的一个架构图，也就是说，我们把波波演算法跟 AI 结合，那它有一半的工作是要在传统电脑上做，那一半的工作呢才在量子电脑上做。那么它做这种最佳化的，在 AI 的学习里面呢，就可以去解决我们在看到的现在已经碰到的一些问题，就可以马上用量子演算法在量子电脑上运作。但是在台湾就很麻烦，因为你是远端连线到别人的，到美国的这一个平台去，所以这个网络的延迟第二个是排队，很多人在用所以我们如果在台湾想要做这件事情的困难，就是连线的这个延迟。所以我们真正在解这个问题呢，也有一种方法，纯粹就回到通用逻辑差，用传统电脑去做。所以目前我们可以看到，勾本演算法可以用量子电脑来做呢，它事实上跟你一台桌机的计算力差不多。而你用你的桌机，也可以用通用逻辑差，让古典电脑去执行它理想上的动作。那在这个理想上的动作本身呢，目前这种变分的量子演算法呢，它是可以抗一些干扰。所以如果你拥有量子电脑，是真的可以做。那台湾当然你就会碰到困扰，因为你是远端连线。好，我们在今年的2月1号到5号在台南有办过这个研习班我们就是教整个的秀演算法，从傅立叶转换 到加法器的设计，到乘法器的设计，跟模运算的设计，最后把它应用在 OSA 的这个密码分解。这是我们今年的2月1号到5号开的班。那本来我们在4月25号、5月1号跟5月8号已经在台北办的 Global 演算法的这一个课。那么5月29号跟30号大概可能很难办，要用线上上课。那我们在这个课程里面就介绍了，通用逻辑差一定要讲，然后讲 Global 演算法，完了我们讲 Global 演算法在 AI 的应用。那么我们也特别提到了这个电脑科技进入人类社会的一个挑战是在什么地方？就是哥德尔的数学上的这一个不完备定理，本来也要讲，可是现在可能要延到比较后面的时间。我们在看这一个量子电脑的发展过程当中啊，我们要看的是它的产业链啊，就是说，如果量子电脑是一个产业，它的产业链有什么呢？有演算法的部分，演算法部分是什么？是它的演算法、程式语言，还有它的编译器。那它的编译器是什么？编译器就是说，以量子电脑的角色来看呢，编译器就是通用逻辑差怎么表达。你只有通用逻辑差呢，量子电脑的硬体才看懂。所以你任何的演算法一定要通用逻辑差来表示，那么量子电脑才会听你的指示去做它的硬体操控的动作。那么在硬体目前啊，我们所拥有的硬体是什么？超导的回圈，有这一个在钻石里面的空切，甚至有些拓扑材料，那都是很高深的课程，或者trap ion 就是把这个离子把它抓住，然后去控制它的这个量子态的改变，或者用光学、用量子光学来做计算。那现在台湾比较希望说，像台积电等等这些公司，因为我们的半导体加工很强，就希望在矽上面去做quantum dot， 就是量子的这个位元的这个操控这个电子的自旋或者原子核的自旋。那目前呢，大概硬体有很多领域。那么这很多领域呢，我们从半导体的经验就知道说，我们要知道半导体怎么运作，有3个东西嘛。一个就是我们资讯科学的人去学演算法，去学程式。那现在传统电脑，全世界自由软体有100多万套，你可以选择你的软体，可是你的软体在特殊的硬体能跑，在另外一个硬体就不一定能跑。那么我们现在所看到的另外一个就是说，它的半导体的元件是怎么工作？这个就是说，元件物理学你要清楚，就是说整个半导体元件是怎么操作。第3个挑战就是说，它到底怎么制造的？所以从资讯软体、硬体的工作原理，到怎么真正去做的制造、制成，这个都是以后它产业链的架构。如果它只有硬体而没有软体，那没有产业，因为软体才真正服务人啊，硬体是把这个工作要做出来。所以呢，以我们台湾现在投入的资源，政府已经说是80亿台币。那比起这个美国、日本或者是中国大陆、欧洲他们所规划的那个，我们是人家的领头啊。那么这个产业也许还需要20年的时间的发展，所以我们需要把学习的精力放在哪里？我们如果都是做制造，那可能我们没有那么多钱。那台湾大概也只能够2、3个团队有制造的能力，可是呢，那团队的人才，还有政府投入的资源，都很难跟国外竞争。我们锦州是跟着人家的脚步， 勉强跟得上去而已哈。那以后要代工才有能力。但是我想这一次美国大概不会希望给台湾代工了，如果有量子电脑的话，除非你比他厉害。所以我们的学习的这个曲线呢，要从哪里呢？要从演算法学进来，再去学元件物理学。那元件物理学不是你想象的那么单纯哦。比如说，你就要学拟态物理、原子分子物理、量子化学、自旋电子学、介观物理，还有数学上的微分几何、代数几何，可能都会用得到。所以这一次量子电脑进入人类的社会呢，它在元件物理学的地方呢，甚至连原子核物理都要被考虑。为什么？那原子核代表的原子99.9%的质量啊，那你要操控原子，那原子核内部的效应可能跟外部的会发生关系。所以这一次的量子电脑呢，它的元件有超导体、有固态物理、有拟态物理、有光学，这个都是本来是应用物理的领域，可是现在全部都要被量子电脑这个研究冲击，或者它倒过来去冲击这些基础原理。那我们就是要去学习这些东西呢，由演算法进到元件物理学，再慢慢去做到制裁。我们的资源一下子全部都投资到硬体，不告开了，就是那个单单一部冷冻机就5000万台币，你哪些单位可以投资几部？但是最后这个产业要形成呢，就是我最后这一张图呢所秀给大家看的，就是说，如果以后有量子电脑呢，它旁边也要有超级电脑来控制它，控制它的这个微波或者电磁波怎么去影响微观的世界。然后呢，它又是很低温，你传统的设备是很高温，界面的问题要解决。那有很多的防灾科技、3D 影像或者3D 列印、高能物理、基因，你可以想象的机器人学这些等等计算的问题，都需要超级电脑来当界面去控制量子电脑。所以，一个国家没有超级电脑的设备，想要去发展量子电脑，成为一个产业服务链是不可能的。这是我们要认知它的趋势。因为量子电脑号称它可以超越传统电脑是超越什么？超越超级电脑能做。那你如果没有超级电脑的国家，你做量子电脑，你要超越谁呢？所以我们的国家的超级电脑要增加才对啊。那以后才可能把这个量子电脑的这一个 A 比生出来啊。那么要服务到产业是很多的，所以我们以刚刚超级电脑全世界的分布，我们大概可以知道说，欧盟、日本、中国、美国是有机会让量子电脑服务群众，因为他们的超级电脑是够的。那我们在做量子电脑开发的时候呢，如果它要成为一个产业链，那还有很多东西要。那我初步先讲到这里，我留10分钟的时间给大家发问，好不好？
线上的学员在听过刚刚黄教授就是精彩的演讲之后，有没有什么问题可以提出来哦？
有问题要问吗？
好像 Google Meet 里面有一个聊天上的问题。
好，这位学员你要自己讲还是我帮你说？好，那我帮你说好了。就是这位学员他是说，黄教授您好，想要请问一个基础的问题，可不可以再说明一次？正转换的部分。
压正转换的部分可以。有没有？好，这个腰正转换是这样，它是由原来的方程式 我们看到有原方程式有一个 h 啊，那这是一个薛定谔方程式，那它有一个 formal solution，所谓 formal solution 就是说它不是真正它的解，而是说形式上的解，它可以把原来的微分方程变成一个随着时间演进的那个算符。我们看到了这个就是这里的 u， 随着时间演进的这个算符，这个算符跟它的这个矩阵的共轭矩阵相乘会等于1，也就是因为它跟它的共轭矩阵相乘等于1呢，我们才称为它的妖正算符，就是说它跟它的共轭矩阵等于是它的反元素了，反矩阵了，因为它乘出来会等于1嘛，所以有这种特性的，它的特征值都是单位元上的复制根。所以我们在做任何的逻辑渣、通用逻辑渣的设计，它基本上都是妖正算符。所以妖正矩阵就成为研究量子电脑必备的工具，线性代数上的复数的线性代数上面的必备的工具，它也是所有的演算法的基础。那它的特征就是它的这个方程式的这个特征值 eigenvalue 都是单位元上的1的次方根，就是这样。不是这样解释，你清楚了吗？所以我们刚刚讲的秀演算法、波本演算法都要用 unit 里的矩阵来表达。那很多人对于量子电脑没办法踏进来的原因，就是对于通用逻辑渣认识不够多，然后通用逻辑渣组成妖正矩阵的方法不会，所以你就很难踏入它的演算法。还有没有其他问题？
喂，可以听到吗？
可以听得到，你讲。
是黄教授你好，我刚刚好像有听到你提到说你们有解决一个问题，然后这个问题在古典的电脑上可能要几百年，然后在量子的硬体上只要几秒，然后你们有一个混合的设备可以在30分钟内算完，想要在这个
好，就这张图
我想问的是，这个半古典的量子电脑模型是指硬体方面的，还是软体的这个模拟器？
我们现在只能做这一个软体架构的设计。那么通用逻辑渣有用到，但是我们有一半的这个输入档呢是要用传统电脑来算，然后呢再输入通用逻辑渣的电路，再算它的结果。也就是说，目前全世界了在解秀演算法，没有人像我们这样用标准方法，就是全部用通用逻辑渣来表达，而且把它解出来。目前没有，我们是唯一一个。我们敢讲50分钟，是因为它要用到，如果你要解到1024个密码，要50多万位元啊！我刚刚没有提到，你要50多万位元，而且没有噪音的。如果要加噪音，那就更多了。所以我们只是提出一个秀演算法，它可以实现在传统电脑跟量子电脑结合之下，就是半古典的这个结合之下，我们去估它的要解1024个位元的这个密码，大概时间是多少？可是我们现实上在 IBM 的平台操作已经在做了 ，IBM 有65个，我们解15就用63个，用掉63个位元，15等于3乘5而已但是我们这样做是全世界唯一一篇，我等下公因为我靠走龙讨假包，他们不是真的秀演算法，他们是已经知道15等于3乘5再去做出来。我们这个是没有，我们这是纯粹就是说用秀演算法的概念，把它的这个模型建立起来，没有办法不用传统电脑。如果你全部都是用量子电脑，它的花的时间比传统电脑还要多。为什么？因为它需要用到傅立叶转换来做加法器、减法器、乘法器、模运算，那会耗掉很多的资源。这个就是一个演算法到一个通用逻辑渣，这是漫漫长路。就像说你有一个演算法要写成那个0101的那个组合语言一样， 就是你想象的这个演算法，如果这个组语言不跟你搭配，电脑是看不懂。所以通用逻辑差俨然于量子电脑的组合语言。我不知道这样的回答你清楚了吗？
是的，理解了。所以是在理论上的可行性是可以在
对对
50分钟。哦，好，
对对对
好，谢
对对对，
谢谢谢。
嗯，还有没有其他问题？
喂，那个听得到吗？
可以听得到。
那个我想问一下，就是半古典的电脑加那个加量子电脑的话，它是那个叫做，因为就我所理解的话，就是如果量子电脑算出来的东西是零跟一的组合，但是到时候要输入进那个古典电脑的话，那个电脑的话是会看得懂吗？还是说我们还要
哦，
做
没有，你这个
其他的？
人要自己操作一次。所以这
哦，
个界面，如果像我们在成大连到 IBM 的平台，我的学生就要从输出档，然后再重建成古典的语言，再放到古典电脑算一下，再重新再输入一个接塔。我们并不是在计算时间上抗正它，而是因为他在美国，我们一等很多人在用，一等一个 data 要 run 2个小时，所以我们现在一天只能 run 5个 data 到6个 data。那如果我把这个演算法全部在古典电脑做，也就是说我们用模拟它是模拟器的角度来看的话，那一个例子搞不好10分钟就做完了，所以一天就可以把一个结果都算出来。那也就是如果你做量子电脑以后的跟传统电脑的界面是一个很重要的课题。所有的科技都一样，界面是最难的问题。那么如果传统电脑跟量子电脑要结合呢？Google 现在就是喊出这个口号，因为 Google 它有最多的伺服器啊，它是超级电脑，那它要做的就是它的晶片要跟量子电脑结合，那它有能耐讲。但是我们如果没有这个能耐的话呢，你只能够在理论上去研究一些课题。你量到了这个0101啊，如果要传统电脑再做，你还是要重新再算一次。那当然，你可以界面语言写得好，你就可以把这0101把它透成你要的公式，在传统电脑算。但是这样一个 cycle 本身在台湾目前是很不现实的。
好，谢谢。
嗯，应该还有最后一个问题吧？
教授，请问一下哈，
哎，
这是最后一页的应用的部分了哈。那就是说，大体来看的话，量子电脑主要在这里面的应用啊，它主要的功能显现的是在哪一方面？这样。
好，以它专属的能耐，它就是解密码学，这个是它的特殊演算法。那么其他的各种演算法，你说我们人类碰到的演算法呢，它跟传统电脑结合的时候呢，它其实任何问题它都可以解，只是说你有没有传统那么大的超级电脑能够跟量子电脑结合，这个硬体的结合困难度是很高。你想看，传统电脑是在常温运作，量子电脑是在绝对零度运作。单单从绝对零度到外面的传统电脑这个界面的温度的转换，就是一个大课题。那第二个难题就是说，你传统电脑里面所碰到的这些问题，希望量子电脑来分工。那这个分工的这一个 input 跟 output 怎么处理，这也是大问题。所以，虽然大家这么热于量子电脑的开发，那可能最快10年嘛，你最慢我不晓得是20年还是30年。但是我们如果都不参与去研究，那可能我们就会跟国际的这个科技脱节。所以这也就是我们面对量子电脑起来的一个困难点。这每一个问题，传统电脑都有答案。有100多万个套软体，难道不够你用？很够用啊。问题是它怎么跟量子电脑分工？这个分工的界面是目前非常难的问题。那我们如果连几个 qubit 都没有，也谈不上什么界面问题，因为我们就没有那个 tool。 所以目前我们的学习都只能从通用逻辑家的角度去看演算法。那下一步就要做到元件物理，至少我个人是安排这样。
谢谢教授。
好，谢谢你。我们看我们的时间已经过了，我的演讲就到这里结束了。
好，那我们再次的感谢黄教授的为我们带来这么精彩的演讲。好，谢谢黄教授。
好，谢谢大家，谢谢大家。
好，谢谢教授给的很精彩的演讲。接下来我们会有 Sony AI 的 Uchenna 来，Sony AI 是东京headquarters 的，然后Uchenna Akujobi 会来演讲介绍他的美食学的项目。欢迎 Sony AI 的Uchenna进来。
Hello, everyone.
Hello, Uchenna. Welcome to SQAI 2021.
Thank you. Everyone can hear me?
Loud and clear.
Okay. So I'm clear to start presenting now?
Absolutely.
Okay. Thank you.
Thank you for joining us.
Thank you for having me. So I don't know, my screen is visible?
Yes, we can see it.
Okay, good. So hello everyone. Thank you for having me here. My name is Uchenna Akujobi. I'm a research scientist with Sony AI. So today I'll be giving a talk on an interesting topic titled Hypothesis Generation with AI. And I hope it will be interesting for you also. So before I move into the talk, I want to give a brief introduction of Sony AI. So Sony AI is Sony's flagship AI organization with a mission of unleashing human imagination and creativity with AI. So the aim here is not to replace humans, but to kind of augment human creativity, to bring out, to empower imagination and the creativity of artists or creators all around the world. So the aim here is for AI to work in harmony with humans to achieve greater efficiency. So the values, our values are one, that we believe that diversity is important for innovation. So diversity in people and methods, also applications, and also AI should be developed in a transparent and fair way, such that it serves for social good. At the moment, there are 3 flagship projects for Sunny AI. This might change in the future, but for now, Sunny AI, we are focusing on gaming, imaging and sensing, and also gastronomy. I work in with the gastronomy team, and that would, to give a brief introduction of the gastronomy project, is that we aim to enhance creativity and techniques of chefs all around the world, so also in the kitchen. And this consists of research and development of AI-powered application and methods for new recipe creation, robotic solution that will assist chefs, assist in the kitchen, and also need human community co-creation initiatives, which will serve as foundation of these activities. So the team, Sunny AI, is led by world-class AI researchers and engineers. And also, we are also eager to work with top talents all across the globe. Right now, we do have offices in Japan, US, and also Europe. So going back to the talk, so the hypothesis, we are talking about hypothesis generation with AI. So first, a definition of hypothesis. So Lexico defines hypothesis as a proposition or proposed explanation made on basis of limited evidence, which should start at a starting point, which should be a starting point for further investigation. So for example, if we have diseases A and B, and we have a drug X, and we know that X is a cure for A, and also we do know that A and B, the diseases A and B are similar in structure and properties. So the question is, since we know that A cures B and X cures A, the question is, will X also be a cure for B? So this could be like a hypothesis which would deserve further investigation. So, of course, we do know that foundation of ideas and expertise are in the literature. So we could get a lot of knowledge from reading published literatures like papers. However, the number of publications are growing in an exponential rate yearly. So doing this manually is going to take a lot of time, and it's going to be tedious. So now the question is, how can we do this in a more efficient, automatic way? And the question is, and the answer is yes. So instead of going to the manual work of maybe searching Google Scholar and then looking at what is done within one by one and then trying to infer something, maybe we could have a system that does this automatically and gives us like a hypothesis. So looking further into scholarly literature, we know, for example, given a literature has different components. So like title, authors, abstract, also citations and keywords. So these are a lot of information contained in scholarly literature, and we can extract some hidden connections or hidden knowledge in literatures. So this is the aim of this work, to try to extract this and come up with hypothesis. So here we are mainly focused on using the keywords, which keywords here could be diseases or drugs or genes, biomedical keywords. So for example, if we have, let's say we have a simple graph like on the left side, where we have COVID-19, MERS, and SARS. And we do know that COVID-19 is related to MERS and MERS is related to SARS. So you have this simple graphical structure, and each of these nodes or each of these terms, we do have like some attributes which could be descriptions of these diseases. So the question could be like, for example, is COVID-19 related to SARS? So this is more like a trivial question, but in our case, we are looking to evaluate also non-trivial connections. So there's kind of not well-studied connections that could be very further apart in a graphical structure. So to do this, we have to extract these biomedical terms, and we do this from biomedical literature data. So for this work, we use PubMed data. We get from the title abstracts of about 22 million papers. We try to extract keywords belonging to genes, chemical, or disease. And also from there, we could also build a graph from this information that we have, so that we know if two keywords are mentioned in the same sentences or in the same title or paragraph. So depending on the settings, we could get a graph which shows this, because right now with graph, a lot of information, real-world information could be represented in a graphical structure showing relationship between objects. So for this work, there have been previous studies. So one method is using ABC models, which says the idea of this is that if A is related to B and B is related to C, then there should be a relationship between A and C, kind of like a triangular model. Of course, this not just simple case, but not just it's too simple to get like complex relationship, but also the computational complexity increasing significantly with respect to the amount of normal and common entities. Also, we do have the machine learning models which have been applied for this problem. But the issue is this, that they failed to include the dynamic relationship between terms, because connections between, so for example, two diseases might be studied maybe 10 years ago, might have been studied 10 years ago. These diseases sometimes don't just get connected. With time, more related diseases are studied together, and then you could see how the connections evolve over time. So the idea here is that if we can understand how these connections evolve over time, we can be able to make better hypothesis prediction. So we do take the approach of graph-based learning. So where we build a graph, we have nodes and edges, and the nodes here would be the terms, and edges showing, in this case, in our work here, showing the co-occurrence relationship between different biomedical terms, and also the nodes have node attributes, which are the description of these terms. So now the aim is that we want to say, given two diseases, or drug and disease, or gene and disease, we want to predict, are they supposed to be related or not? Are they related or not? That's the prediction we are going for here. And the goal here is to learn from the graph structure and attributes, and we learn latent variable H in such a way that it contains enough information to make future connectivity prediction. So for example, like I said here, you could want to see, we know SARS and COVID-19, should they be related? Of course, this is a very trivial case. So, like I mentioned earlier, our aim here, we want to not just take a graph and then try to predict. No, we want to understand how this relationship build over time. So we formulate this in a dynamic graph setting. So where we split the graph into kind of temporal segments, where we have a graph of connections made till 1949, and then the next graph section would subgraph would be from 1950 to 1959, and so on. So we observe how the connections made with time, and then the question is, can we infer for the next time window? So it could be like 10 years window or 5 years time window. What could be the new predictions? And in this case, we are not just looking at temporal. We're not looking at transductive setting. We're also looking at inductive settings where you could have for example, new diseases coming up. So yeah, so now, yeah, like I mentioned, we are looking also into like not just transductive but inductive. So now the question is, what about unobserved links? So if you look at the example on the left, so we know that node 1 and node 4 are linked in G3, so, right? And then they were not linked in G2, which is at the time 2. So now the question is, how about 2 and 5? Are they supposed to be linked or not? So we are trying to predict for G5 if 2 and 5 are supposed to be linked. In this case, we could say, like, for example, if 2 is a disease and 5 is a drug, we could want to say, should they be studied together? In this case, is there a possibility that there is some relationship between these two items? So there are two ways we could formulate this. So we could have this as a positive negative learning, where we say if we do not observe any connection, then we should assume that it's a negative connection. Of course, a lot of works have used this, but this is more like a closed word assumption, which might not really hold well in real world scenario. So another way is to look at it as a positive unlabeled learning, where we say all observed links are unlabeled. So we don't want to kind of put any strong assumption that is negative. So we want to leave it as unlabeled, but at the same time, we want to learn from both the observed and the unobserved. So for the unobserved, we say it could be positive, it could be negative. We do not want to make any strong assumption on that. So this is the positive unlabeled learning case. So we formulate this problem in a dynamic graph learning structure. So we split the graph into subgraphs in time frames, time windows, and then we kind of learn how these connections, how the connections are made over time. So we have like more links forming over time and new nodes coming in over time, but we do not have links being removed. So the aim is to infer the labels of the unobserved pairs. So with that, we could make kind of like it's like a hypothesis if two terms, node pairs should be related or not. So for this, we built a recurrence model, which is, since also we are looking at this as a temporal graph, dynamic graph. So we built the recurrence model, which kind of first it takes the first time step, and then it updates the information over time as it takes the next time steps and also next time step. every time updating the information it's gathered. And at the end, we want to say, based on the information that we've gathered so far during these time steps and the previous time steps, should these two nodes, for example, be linked or not? So I'll give more details about the model. So the recurrent update block is basically a sesame network, kind of like a sesame network, where you have, if you're trying to look at node pair VI and VJ, so we have FG, which is the aggregation network. We take information for VI and VJ. We learn some embeddings ZVI and ZVJ for each of these nodes, each of these terms, and then we aggregate this information, and based on the aggregated information we've observed at this time step, we update the general vector, general embedding, which is the HAIJ, which is kind of containing information of all these previous time steps that we've gone through, and then we update it with the current time step, and then we pass it along to the next time step. So for the aggregation network, it has graph search, which is, it tries to aggregate information from the neighborhood of each of these nodes, and then using a method known as graph search, and then based on this aggregation, it comes up with the final aggregated information, which contains information of this node and its neighbors. So yeah, so in PU setting, it's a little bit easier because we just assume that everything not observed is negative. So we could just have a soft sigmoid function to predict if a node pair is related or not. But when it comes into PU learning, it becomes a little bit more complicated because we can't just say that an unobserved pair, it should be negative. Right, so in this case, we use the PU learning method. We use weak estimation, where we can rewrite the negative part to be able to use this unlabeled pairs. So we write this and we write it using this method. And then if you look at this using the risk estimation, we see that the pi p, which is the positive prior, is quite important. Right, so now this positive prior is, in simple terms, is the ratio of positive pairs in the whole data set. This actually, it's hard in real world settings, it's hard to estimate, to calculate, because actually, since we say the unlabeled pairs could be positive or negative, we can't really calculate this value directly from the data. Some works, they try to set out some validation sets where they use the calculation on the validation sets to estimate this. However, we are looking at real world situations where we don't have this liberty to get this validation set. So in this case, we need to come up with a way to estimate this positive prior. And we use a Gaussian mixture model, which is based on variational inference model. So the aim here is that if we can have two components, so we assume that the data is made up of two components. So one is the positive component, and the second one is the negative component. So if we can estimate these components, then we can calculate the positive prior based on the component weight. So we do this using operational inference model. I don't want to go deep into the details of this, but if there is any question about this, I would be happy to personally answer that. So yeah, so for evaluation, we evaluated this on 3 data sets. So COVID-19 data set, which is we built a graph of COVID-19 terms found in papers working in COVID-19 under COVID-19 problem, and also you have the immunotherapy and the virology. And this is the statistics of the data sets we used. For the previous settings, we see our proposed method, which is the TRP method. We found out that in most cases it outperformed the baseline models. This shows that actually it shows 2 things. That's one, it's learning from the dynamic problems, the dynamic settings, how this, not just the graph, but also we'll try to learn how the connections are made over time. This improves performance. And also learning using PU methods where we don't make any strong assumption on the unobserved pairs is also good. So we do some go test cases. So we go test cases for most papers working on hypothesis generation at this. And we try to see, can we make this prediction, this hypothesis, before it is studied. So we found that each of these 2 pairs of keywords, we try to evaluate what year we could predict this, and also the original discovery year. So for example, if you look at renal disease and fish oil, the original discovery year of the relationship between these 2 was in 1985. And we could see that we could, using the data that we have from 1970 to 1979, we could actually make this prediction way beforehand. And also the same for migraine disorder and magnesium, and also the others. So yeah, this shows that what we built is able to make this hypothesis on time. And also we try to show that the importance of temporal modeling. So not just giving a static graph, but learning how these connections are made over time. So we could see that over time, the model, it keeps improving in result, in its performance, compared to other models which are kind of going up and down. So this shows that our model learns from the periodic addition of new data to the old ones and updating. So just learning how these connections are made again. So also, of course, we try to have like a qualitative evaluation where we try to look at the current, COVID-19. So we want to see, could we make a prediction about COVID-19 before, let's say we just knew about COVID-19 right now, and we have information about what has happened till 2000. We had 2 settings, so we trained to 2015 on data that we obtained to papers published 2015, and then we tried to make a prediction about COVID-19. Of course, in this case, we see that COVID-19 is a new term, so COVID-19 wasn't available in 2015. So it's kind of like an inductive setting. So we tried to make this prediction. And also we trained, second setting is we trained to what we have in 2020. And we tried to make also the same prediction about COVID-19. So the prediction here is that I want to see what are the top terms that the hypothesis here is that what are the top 10 terms that should be studied that might have relationship between COVID-19. So for the one study for the evaluation on graphs to 2015, we do see that the top ones could have we have leukocyte count, fever, hand, air, lungs, SARS. So we could, and we also try to evaluate, is there any existing relationship between these keywords and COVID-19? And we can say that yes, there is connections made. Yeah. So for all of them, there were connections between COVID-19 and these terms. Then for the ones trying 2020, and we try to, so for 2015, we evaluate on the data we have till early 2020. However, when we train on all the data we have, of course, it's kind of like trying to make a prediction. We do not have the testing. So what we did is we tried to manually evaluate this prediction. And we found that for most of them, we could find a relationship between COVID-19 and the terms itself. So it kind of shows the model is able to learn to make good hypotheses for new unseen diseases. So for future work, we'll aim to extend this to polarity prediction. So we are not just trying to say if there should be a relationship between these two nodes, but we want to say what kind of relationship. So is it like a positive relationship? For example, this drug would be a cure for this disease, or maybe this drug would be bad for this disease. So instead of having, okay, should they be related or not? In this case, we are trying to understand what kind of relationship are there. Also, we would want to see the strengths of relationship, the relationship strengths. So this could be as a regression tags. So also we want to predict with explanation, which is something we are already working on right now. And kind of generate a real hypothesis that is more understandable than just should they be connected or not. But we want to understand why should they be connected. So kind of have an explanation for that. Also, possible application for gastronomy is we could have ingredients pair prediction. So we want to see which ingredients goes well with what ingredients. Right, so with that, you could come up with new recipes or new tastes. And also, of course, recipe generation. Also explaining why this ingredient should go well with this other ingredient. So for example, we could say sake and chocolate goes well when eaten together, or maybe mix sake and chocolate to get a new sensational flavor. And of course, also this could apply to if you can have a fusion between biomedical hypothesis generation and also gastronomy. So we could have a health-focused recipe recommendation, creation and modification for this. So these are the possible applications. So I would like to thank you all for listening. And before I go, I would like to encourage you to join Sunny to unleash human imagination and creativity with AI. Thank you very much. I don't know if you have questions. I can turn on my presentation. Oh, how was the gastronomy project implemented? Well, the gastronomy project here is more focused on we want to see how we can help chefs and to improve creativity. So how can we have AI augment the work of humans in order to lead to better efficiency? So that's how the gastronomy project, I believe, came along. So also I would encourage you to go to Sunny AI website. We do have more information and also some videos of chef interviews that could give more insights. Sorry, quite, we have a large number of people. So we have right now branches in US and Europe and also Tokyo. So there are quite a lot of people. And we are still interested in hiring more talents across the globe. I believe right now it's possible. Could just send me an email and we could discuss from there. Thank you.
Uche-san, thank you for good, wonderful explanations, presentations. And then like the students that want to hear about your project more, like gastronomy, could you please explain a bit more about your project? If it is not confidential.
Yes,
is it confidential?
Yes, it is actually confidential, but in general, the project, it's more of like on the website says like trying to augment human efforts with AI. So to help out in the kitchen, in the sense that we want to see if we can, like on the website said, if we can come up with methods and applications to help in the kitchen, help out the chefs, not just chefs, but I mean everyone cooking in the kitchen. So in details, it's more confidential. I'm sorry about that.
Oh, okay. So is it okay to ask a bit more, like the Taiwan and then like Japan is different from the company cultures, and then so how like the Sony AI implements the AI like the technology into the like a society, like the how like the Taiwan the AIs that implements their AI techniques into the society, it might be different from the Japanese way. So if you feel like something like the once you like the working like a Sony AI, so could you please explain about the cultures or I'm sorry about the abstract question though.
No, I understand. So I will try to answer, and I hope I answer the question correctly. So first, I would like to talk about the work environment in Sony AI. The works environment Sony AI is very, I would say I do enjoy it because it's more about everyone knowing what they have to do and then collaborating to achieve this goal. So the work-life balance is very good. You get your weekends to rest, and also you get to work with bright minds, which is something exciting that you could see everyone coming together to build something that you know will have a social impact in a good way. And how the AIs are integrated to the society, I believe this is more of we try to create something that is useful for everyone. Of course, not have negative social impact. Right? So I don't know how it works in Taiwan, but here the aim here is, of course, we have if you look at the ideas of Sony AI, we aim to make sure that whatever we create is fair and transparent, such that you could actually see how it's made and you really know that there is a social impact in whatever you're working on. I don't know if I answered well.
Yeah, thank you for the nice explanations. I'm wondering if like the National Taiwan University students that want to hire Sony AI, how can they like proceed to it?
Oh yeah, so you could if you go to the website, you could contact, and also LinkedIn. One of the on LinkedIn is very, you see we do post like job openings on LinkedIn, so you could also go through that.
Okay, thank you. So if other like Taiwanese students or the professors have the questions to him, yeah, it might be the rare to like ask like the researcher in Sony AI, I think.
Yeah, I think a lot of people would be very interested from NTU Computer Science and Information Engineering, CSIE, and our EECS college in terms of, replying to AI, Sony AI. And Sony AI was created last year, is that correct?
Yes, 2020.
So I remember I saw on LinkedIn that you guys were celebrating your 1-year birthday. Very new, and it's 前线科技, as we say in Chinese, the front end of cutting edge technology. And actually, in terms of having follow up, I wanted to present a little bit about a topic called superintelligence for our Symposium for Quantum AI for SQAI. By the way, we like to call it SQAI. It sounds a little bit like, in terms of 天空 SQAI. So superintelligence is a topic I've presented a couple times. Here, I'll share my screen really quickly, and the entire screen. And thank you again, Uchenna, for joining us for SQAI. So I want to confirm, can everyone on Twitch hear me? Here, let me double check. Checking on my phone here. Afterwards, we're also going to have Professor Hu Zhongxing, Professor Alex Hu, to present starting at 6:30. And okay, looks good. Looks good. Okay, cool. So superintelligence in Chinese is called 超级智慧. By the way, I wanted to confirm, can everyone see my screen?
Yes.
Okay, cool. So yeah, superintelligence is called 超级智慧, 超级智能. And recently I read fairly recently, I read 4 books on this topic. One of them by Nick Bostrom, by Li Kai-fu, as you guys might have heard of Max Tegmark and Ray Kurzweil. Some of you guys might have heard some of these titles. But essentially, this wording, calling it superintelligence, it started out with this book one on the top left by Nick Bostrom, Superintelligence, and the actual full title of the book is Paths, Dangers, Strategies. Highly recommend it. Actually, out of all 4 of these books, what I recommend the most would definitely be Life 3.0 by Max Tegmark. Now, Max Tegmark, I'm going to allow this person to enter really quickly. Okay, Max Tegmark, he's an MIT professor, and he's working actually with Elon Musk on what's called the Future of Life Institute, and that was created and funded just very recently. Max Tegmark got either 5 or 10 million, actually $10 million from Elon Musk in creating that institute, and some of the top machine learning experts in the world have joined it. And we also have How to Create a Mind, which kind of goes a little bit more into the technicalities of how the brain works and how we could replicate, how we could upload our minds onto the internet, how we could do all these crazy things. And AI superpowers is more in terms of country power. So, for example, China and America have the most data in the world, and therefore are able to create AI that is driven by the most data and create some of the strongest models. What is this going to result to in the next 5 to 10 years, in the next 20 years, in the next 30 years? So it kind of makes some relevant predictions there. Let this person admit into the talk. And okay, cool. So essentially, I'm just going to skip over this. I did on my Medium page. You can go to sethharding.medium.com for that. I'll send the link later. But I wrote a couple articles on it. Quoting Elon Musk here, he says, non-overseen development of AI is a humane species level risk. So what does that mean? I'm going to get to kind of the implications of that. So Life 3.0 by Max Tegmark. What does Life 3.0 mean? Well, we have Life 1.0. Life 1.0 is life that evolves its hardware. So, for example, it's our biological body, our human body, and software. And so we use basic tools that leads directly to Life 2.0, and that's called the cultural stage. And Life 3.0 is when we're able to modify both the tools that we use, the software and the hardware, so the actual biological structure of maybe potentially our minds, maybe we could convert our arm into some sort of robotic arm, and we can all become cyborgs. And it's a very nerdy topic, but it's also a lot of fun. So we have 3 categories of intelligence: artificial narrow intelligence, which is also called weak AI, and that's essentially referring to what we have now. We have weak AI, and that is intelligence within a specific domain, such as Go or chess, or you name it. It's intelligence within a very specific field. Now, we also have artificial general intelligence, which refers to, which is abbreviated to AGI. It's human level AI. It's basically the application in a broader sense of having a bunch of different applications of weak AI. So if you have tens of thousands or millions of different applications of weak AI and you combine them all together in a fluid and intelligent and applicable way, then potentially you could have artificial general intelligence. And now it's not hard to see, it's not hard to picture that after we're able to get artificial general intelligence, it's not a large step to jump to super intelligence. I'm going to turn my camera on. Cool. So, and there's this concept called singularity. And singularity is essentially the concept of we have this intelligence explosion. And so we start off with this artificial narrow intelligence stage that we're at right now. We gradually move up to application after application of AI that boosts artificial general intelligence. Now, this is something that a lot of different authors have been explaining, with the so-called exponential growth rate of AI once we get to this stage, right? So if we're able to make AI that is able to improve itself in any way, well, then that improved version of itself will then be able to improve the mechanisms with which it uses to improve itself. And so in that way, it's going to improve itself in a faster and faster way. So the way I explain it, which none of these authors have done, is the faster a computer improves itself, the faster it is capable of improving itself. Moreover, the faster a computer is capable of improving itself, the faster it will actually end up improving itself. So it's a little bit philosophical in some sense, but it can also be explained in a more mathematical sense. Now I'm going to jump over here to what is intelligence, right? What are we saying when we talk about intelligence? It could be the capacity for logic, it could be problem-solving skills, it could be creativity, it could be planning ahead or risk management, different types of plans, EQ, emotional quotients, IQ, intelligence quotient, or any or all of the above. There are many definitions. So how do we converge on one specific definition? That's one of the main topics that these books are discussing. And now we have this question: is superintelligence safe? Another question: are we safe from superintelligence? If we have, in other words, if we have superintelligence, is the world going to be safe? If we have this, this robot or this computer that's able to self-replicate, that's able to increase its intelligence far beyond that of even the brightest human minds in history of, Isaac Newton or whatnot, how are we able to control it? Are we going to be harmed by it? Is it going? A lesser question would be, would it be harmed by us? Now, there are a lot of different scenarios that these futurists, these authors who are also futurists, that they illustrate. One of them being libertarian utopia. And essentially in libertarian utopia, you separate into three zones of society. So you have machines only, and these and it's the most advanced zone with the most advanced technology. And then you have cyborgs, which are the people that accepted kind of this new society, and they're like, okay, now I want to advance my body or whatever. And then we have the human only zone, which is kind of like the more traditional, more maybe a little bit more conservative in terms of accepting the new technologies, and that they want to live a more traditional life. We also have so that's libertarian utopia. And there's actually, in terms of libertarian utopia, there's actually a large emphasis on protection of personal property, and that's especially in the human zone. So there's no crossing between these zones. Then we have benevolent dictator, and benevolent dictator enforces the laws that are set by humans in order to ensure happiness. Now, how do we define what is happiness? There's something pretty funny about this, is that happiness could be defined as a function of serotonin and dopamine. And so if we tell a machine, I want for all humans to be happy, and we set that as the goal for AI, well, that could, as Elon Musk had pointed out in an interview 2 years ago or so, that could result in something that we didn't expect, and that is that machines capture all humans and then inject us with large amounts of dopamine and serotonin. Well, there we go. Now we're all happy. Is that what we wanted? No, exactly my point, which is, how are we going to define the goals of AI to make it to have zero ambiguity, and make it so that the AI is serving and helpful for humans rather than the other way around? And so there are all kinds of these different scenarios. There's gatekeeper scenario, and in the gatekeeper scenario, maybe it's a little bit harder to detect where the AI actually exists, and where it was successfully able to implement itself. Sorry for kind of jumping back and forth between the slides and the Google Meet. There's protector. Its top priority is to avoid being detected, kind of similar to Gatekeeper. We have Conqueror, which is kind of what most of the movies are going to be talking about, things like Terminator or whatnot. AI overpowers the humans and ends the human species. Max Tegmark, he actually, in his Life 3.0 book, he actually goes over a lot of different scenarios where we can actually use superintelligence to explore space. And space exploration with AI is not really a new topic in terms of science fiction, but in terms of talking about realistic, well, some people could call it pseudoscience, and maybe it is on some level. And on some level, maybe it's not. Maybe it is actually a legitimate futuristic topic that we can be legitimately discussing, just in the same way that 10 years ago or 20 years ago, we would be saying that talking about AI safety is a pseudoscientific or science fiction topic. Well, now it's not. It's a very important topic that all companies, for example, Microsoft, for example, Sony. I know that Sony AI is now hiring AI ethicists as well. It's a very, very important topic to be able to discuss. How is this machine model that we're creating, how is that, able to bring good to humanity? And how is it, for example, how are we going to make it AI ethical? So, for example, law enforcement or you name it, so that the business is not exploiting humans in some way. That's a very, very important topic that was not being talked about 20 years ago, but it certainly is today. Then we have something called the descendant situation, the descendant scenario. And it's caused by having robot kids. And yeah, I kind of point out right here that my initial reaction to this would be, wouldn't it be more gradual than, in terms of like human extinction and transition from human to robot, wouldn't it be more gradual, such as in like just uploading our minds that are subsequently, altered on the machine, not altered in not physically altered. Or you could just have like gradual reconstruction of the human body. And actually there's some concepts of teleportation that kind of go over that as well. And so I kind of point out here, so you'd go from human to a human plus a simulated mind, which means that you'd have a simulated mind of a human being, as well as the human being in parallel. And then once the human has reached its lifespans, then you only have the simulated minds. And then another path would be human to cyborg to fully robot. A lot of these are, these are definitely more science fiction topics right now, but some of them are a little bit more likely than others, I would argue. And then there's also one final scenario that I'm going to point out here. There's actually a lot more in Life 3.0 that are discussed, but there's also one final scenario that I'm pointing out here, is that zookeeper. So essentially, just in the same way that maybe humans put animals in a zoo, well, now the robots are going to put humans in a zoo, and it's pretty much kept for history or something like that. And it tends to the simplest needs of a human, physiological needs. So our habitat, our food, whatnot. It's a goofy little situation. But anyways, here's another concept that I'm going to talk about. Can superintelligence break free? Now, MIT CS Computer Science just released an interesting paper using formal languages and automated theory to prove that there's no way that you can guarantee that a superintelligent machine is able to prevent superintelligence from breaking free. Now, and this again is one of the most important and most discussed AI safety and ethics questions. And in Life 3.0, there's this group called the Omegas. Now, the Omegas are kind of this like private entity. They're developers, and they create this superintelligence, and they try to find all of these different ways of using the superintelligence to make a bunch of money. And so they develop a bunch of different weird companies, like, for example, one that automatically generates animes or something like that, or cartoons or movies and videos, and they get a bunch of money from that. They also make the super intelligent stock prediction. If I remember correctly, it's like the super intelligent stock prediction, which gets everything correct, and therefore you can make a lot of money out of economics. be able to fairly accurately predict the future. Now, how does this superintelligence, which is to begin with boxed up by the omegas, how is it, so how is it made so that the superintelligence breaks free? Well, the superintelligence is so intelligent that it's able to trick one of the omegas into releasing it in a very kind of underdelving way, in a way that was not expected at all, by pretending to be it sounds a little bit goofy, but they actually give a pretty good backstory to it. And that is, give me 1 second. I believe it is when they simulate one of the Omega's developers' wives in the computer, and then like, this is my data, and then they trick that Omega member into giving the password for that machine, for the machine that it's boxed up in. And once it's able to make one copy of itself, then it's able to break free. As long as it makes one copy of itself, of its software, that's all it needs. One copy of itself on a machine that has access to the internet. Then it can replicate itself thousands and millions and billions of times over. Now, we're talking about AI safety. One of the kind of biggest contributions in the last century to this field has been by Asimov, and it's called the 3 laws of robotics. Now, the first law essentially states that a robot may not injure a human being, or by inaction allow for a human being to come to harm. So what does that mean? For example, if you have it where AI is able to, I'll give a pretty basic example actually. I'm sure everyone has heard of the scenario where an asteroid its trajectory is heading for Earth. And what are we going to do about it? How are we going to prevent it? How are we going to prevent it from making a devastating collision to Earth that ends all human life, that destroys the ozone layer, whatnot? If we have superintelligence that is able to prevent this situation from arising or from happening, then by the first law, and in fact by the second law potentially, and essentially by the second law as well, we're able to. We need to make sure that the robot is able to prevent that from happening. Now, it could also be more of a direct way. For example, if we're talking about AI weaponry, AI weaponry is one of the biggest topics right now in AI safety. And so, is the future of human warfare going to be with AI weaponry? So, for example, drones that are autopiloted, that are not being supervised by humans, and automatically detect who's the enemy, who's the friend, who's the ally. That's a dangerous topic. Now, we also have the third law, where a robot must protect its own existence. So essentially, it prioritizes, of course, human life before its own existence. So long as that doesn't conflict with the first or second law, which is kind of giving it the priority. And afterwards, Asimov realizes that his law isn't comprehensive, and so he adds law 0. And so law 0 essentially states that a robot may not harm humanity, or by inaction allow for humanity to come to harm. But even this is not comprehensive enough, and it still leaves a lot of room for ambiguity. And so kind of the goal that I'm getting, kind of the idea that I'm getting to, is that goals in AI can be extremely hard to program. How are you able to simulate every single situation that a robot is able to, that a robot is going to face when it's trying to get to its final goal? So if you give it a final goal that's as ambiguous as, well, I gave one goal, and that is the human happiness function or whatever. Then what if we say we want to explore the entire galaxy? Well, Max Tegmark, in his book, he talks about something called computronium. And computronium is this theoretical substance where it's at the absolute physically the most efficient physically possible structure. It could be through quantum computing. In terms of a matter structure that is used for computation. And I would argue that is going to be achieved through quantum computing rather than, of course, rather than through the traditional silicon computing. There's also optical computing that's coming out, the topic of it has been discussed in MIT Technology Review recently. Saw a very interesting article on that. I'll get back to my main point, is that goals are extremely hard to program. Now, I was making the example of, we give the goal of AI to explore space. Well, what if it decides, look, I'm going to use all of the substance, all of the matter in the universe to maximize my computational resources. And what if it sees humans as being an obstruction to its goal? Then maybe it ends human life in the meantime, in order to achieve that goal. Or what if, for example, now this is an example that all of these authors give, almost all of these authors give, and it was originally proposed in the superintelligence book. And that is that we have it where we give AI a very simple goal of creating paper clips. That sounds very ridiculous, doesn't it? But it can be such a good example for showing how ambiguous these goals can become. What if the AI sees that in order to maximize its capabilities to create paper clips, it has to take over all of the human-created factories in the world, or it has to take over all of the human resources in the world, because it's just maximizing, right? So we define this ambiguous final goal, but along the way we have to define what it's supposed to do in order to get to that goal. And the problem is we don't have any way of defining all the situations. There's just no way. And so we're going to have to make it, well, some people might argue that we're going to have to go back to rule-based AI in a certain sense, in order to make it so that it's able to be prepared for all these different kinds of situations. And I talk a little bit about here. I'm not going to get into the technicalities. I had presented this a few times before with MIT's paper, but essentially what that part is talking about is that computability theory, like formal languages and automated theory, does not answer the question of whether an intelligent machine will harm humans given specific circumstances. And among the billions of programs that are currently running, there's no guarantee of the absolute safety of each program. And so what's the solution here? Most experts are going to say that oversight programs will be able to effectively monitor and guide future development of AI, and hold the developers and the organizations that are behind it accountable, holding them accountable to ensure safety. And there's this growing movement now that's pointing out that we need to be able to have open discussion on this, and we need to make it so that not only are AI developers involved in this discussion, but people of all backgrounds, people from everywhere in the world, people from from economics, from government, from you name it, every single field need to be involved in the development of AI in order to ensure that AI is actually representing everyone's goals rather than just the goals of the developer, like you see in Max Tegmark's Omega's situation. And that's where AI ethics comes into play. And Microsoft is actively promoting responsible AI development, putting people first through fairness, through reliability, through safety, privacy and security. And I was mentioning about inclusivity, transparency, open source, and being able to hold developers and just AI developers in general and their constructions accountable. And that is my presentation on superintelligence. And now, since we still have a little bit of time, I'll give everyone a little time to ask any questions if you have any. And after that, I'm going to give a brief introduction to our club, to NTU AI Club. And so feel free, don't be shy, feel free to leave a message either right now or during my second presentation. Don't feel embarrassed to interrupt me. Just you could raise your hands. You can, feel free to interject anytime. So any questions? If not, I'll begin within about 30 seconds. So in 2019, a few students from NTUCS created NTU AI Club. And this is one of the original logos that we had created. We also created something called HixLab. This is our newest logo. It's called AI Bot. He's a fun little guy. It was created by Xie Mingfeng. He's a PhD student in NTUCSI. And you'll see this kind of plays into the topic of natural language processing. 自然语言处理. And this is A, this is when. This is also technically the logo that's used for Google Translate. But yeah, the when character. I mean, it looks a little bit like AI. Yeah, it's just a cute little robot. And yeah, so this was a presentation. So I'm a fourth year, second semester. I'm serving as a president currently, and we're actually going to be having elections for our second day for the SQAI event. That's going to be in 9 days from now. So on Saturday from the exact same time, 4 o'clock, all the way until 9 o'clock. We're going to be discussing, again, a lot of really interesting topics. We had our NCKU professor, and we had our Sony AI speaker. We have the NTU AI speaker, and as well as professor from Zhongyang Daxue. And we're also going to be presenting a little bit about businesses and smart contract research form a little bit later as well. And my research background is in blockchain. I've done a little bit in medical analysis with a company called Reliance Biosciences. And near the end of this event, today I'm going to be introducing Reliance Biosciences. You guys can go check out their website at reliance-bio.com. I'll just quickly write down that, I'll just quickly send a message with their website. Oh, and by the way, 1 second, let me see here. Let's see. Okay, cool. Looking good. And by the way, one of my favorite topics for AI is definitely astronomy, and how we can kind of use AI to define and describe different stars or automatically give classifications to different galaxies. Another big topic that I like to research about is how we're able to identify fake news. And of course, what I was mentioning about AI ethics and safety. I also like doing a little bit of research on, for example, NVIDIA's hardware. And I've worked for a company called AD-Link, which works fairly closely with NVIDIA hardware. And I was working on their natural language. I was actually working on how to optimize natural language processing on, for example, edge devices. And I've also done a very little bit of work on reinforcement learning with a couple of my classmates in ABC Labs, also called 海大公司实验室. Now getting back to the club here, this is the older architecture. We found that this is a much more efficient architecture. I keep saying it wrong. And so we have the president, the vice president, and the advising professor. We have here the AI department, the administration department, and the communications department. The head of the communications department is Zhao Yunxiang. He's Henry Chao, and he's one of the best in terms of PR. We also have Xingzheng Buzhang, and that was Desheng last semester. Now it's Gongfu So. and AI 部长李哲宇and now the 副社长is 余德璇。Our 指导教授, our supervising professor is Liao Siwei. And actually, Liao Siwei is also going to be having a presentation at SQAI Day 2. So make sure to stay tuned for that. Now, in terms of AI Club's relations to other clubs, AI Club has relations with Blockchain Club, but actually Blockchain Club, its name got changed to Into FinTech and RegTech Club. And so I had the opportunity to give a mini presentation yesterday. Maybe some of you guys saw that about Smart Contract Research Forum with NTU FinTech and RegTech Club. You guys can check out their Facebook page, and their acronym for their club is NTUFR or NTUFRC. There's also NTU Open Source Community Kaiyuanse. I've been there before, and there's also Data Analytics Club. Now, the difference between Data Analytics Club and AI Club, the main difference is that Data Analytics Club focuses more on the data aspect of it. So how are we going to become data scientists? We focus more on the AI programming, nitty-gritty machine learning, while they focus on, for example, Excel, on how to optimize the data that's going to eventually be fed into the AI model that we program. And then there's also 台科大资讯安全社, and that's NTUST Information Security Club, or you could call it Cybersecurity Club. These are just some of the the tech clubs that are at NTU and in the NTU system, because NTU has 师大、台科大跟台大. Here are some of the sponsors, some of the people we've worked with. We've worked with Roxai, who's the CTO from DBS. We work closely with 亚太区块链发展协会. We work with Reliance Biosciences. We work with Past Lab Performance Applications and Security. And of course, our 指导教授is ABC Labs. And our main speaker, Hu Zhongxing, he works at Big Data Spark, and an expert in machine learning. And here's some of the meetings that we've had in the past. A lot of fun ever since 2 years ago. And this is with Hu Zhongxing and DBS, as well as the AI Club staff. Just having fun. It's just a bunch of meetings that we had. And here's a machine learning class that we had a couple years ago, and it's been a lot of fun, and it's been a great time. And please do join our club if you guys are interested in learning more about machine learning and about quantum AI as well. Hu Zhongxing is an expert on quantum AI, and I'm presenting a little bit in terms of Microsoft Learn. I'm just going to skip this presentation really quickly, but I would highly recommend you guys check out LinkedIn Learning for online classes for the summer. You can put that on your resume. It's got world-class content on it for every single topic that you can imagine. And of course, Microsoft's subsidiary is GitHub. Now, Smart Contract Research Forum, we use GitHub every single day. We have a document pipeline that essentially publicizes all of the information in terms of the proposal stage for different research summaries. We put everything on our GitHub page, and that is for it's most likely for GitHub. And so that's kind of a brief presentation that I wanted to give on AI Club and on superintelligence. Now I'm gonna give about a 15-minute or so interval between this presentation and the next presentation to give everyone a little bit of a break before the next lecture, before the next speaker. So yeah, if you guys want to get some food, if you guys want to, I'm going to admit everyone here, if you guys want to get some food, if you guys want to go to the bathroom, if you guys want to go take your dog for a 15-minute walk, feel free to do so right now. And we're looking forward to next speaker, Hu Zhongxing. So thank you guys.对，就是说我们大概会给大家15分钟来休息一下。如果你要上厕所或者遛你的狗，或者是你要吃晚餐的话，就 现在可以到6点半可以休息。对。
Hey, Seth.
Hey, Professor.
Yeah, can you hear me?
I can hear you.
Yeah, good. 6:30. So it's still 16 minutes to go.
Oh yeah. So we're giving everyone a little time to, because we started at 4 o'clock. Oh, here's someone's joining us.
So how many people here?
So far 76. And we also have a Twitch live stream.
Okay.
77.
So you're recording. Seth, are you there?
Hello.
Seth?
Oh yeah, I'm using someone's computer right now.
We started or just...
Oh yes, feel free to begin whenever you are ready.
Oh, okay. I see. I'm waiting for you. Okay.
Oh, thank you.
Okay. Hi, everyone. My name is Chongxing Alex Hu, and it's my pleasure to give the following presentation regarding this topic, from Shannon to Feynman, an introduction to quantum information theory. Okay. Okay, this is the outline of this today's talk. Okay, what we are interested in is about the quantum information science. Okay, now it includes the three different fields. One is from the quantum theory, the other another one from the computer science, and the last one as the information theory. So now this is a brief timeline regarding this development. And in 1920s, quantum theory, that's the onset of the quantum theory development, and a few of the pioneers like Planck, Schrödinger, they started this research field. Okay, and then in 1930s, we take a look down here. You can see the Turing machine, which is the something regarding the information, some information errors, and Alan Turing proposed the one idea how to design something something we can store the data and also the process data, and he called it the Turing machine. And in 1948, Klaus Shannon he proposed one mathematical model. It's regarding the communication first, but actually nowadays we call it information theory. Okay, we are going to talk about it later. And then in 1965, Richard Feynman he won the Nobel Prize with in the field of the quantum mechanics. And then in 1982, Feynman proposed a new way to do the computing. He called it the quantum computing. Okay, that's 1982. And then in 1994, there's a professor, Peter Shor, gives the first quantum factoring algorithm, which shows the you can really can solve the problem. Okay, so now let's talk about the Shannon. Okay, something about Shannon. Claude Shannon, he was born in April 30, 1916, and actually he won his he earned his degree in mechanical engineering at the University of Michigan, Ann Arbor first, and then he went to the MIT for his master's degree and PhD degree, both in mechanical engineering. Now you can see here, he is a renowned American mathematician and also the electrical engineer. And also you can see cryptographer. Okay. Well, the point is, in 1948, he proposed the mathematical theory of the communication. And after that, the people recognize him as the father of the information theory. Okay, and there's one thing I would like to point out, that is he is also well known for founding the digital circuit design theory in 1937, and he is very first person using the Boolean algebra to construct the logic gates like AND gates, OR gates, and NOT gates. And it's in his master thesis. Okay, so he is a guy in several different areas, and he reached the following classical information theory in 1948. Now, his interest is, suppose we have two persons try to communicate. For example, like the Alice and Bob. And Alice tried to send the document to Bob. Now, this original document, in the if we try to send it out, we have to send it out with the digital signal. So you have to do the encoding, which means we need to change it to the binary system, like this one. Okay, so you change this one into the binary system, like the binary files. So we can use the digital signal to send it out. But problem is, we have the communication channel here. Most likely, there is some random noise, which means it will change the signal, okay, alter the signal. So the point is, how could we know the document or the digital signal being changed or not? Okay, so that's the uncertainty for this issue. And then Shannon used the entropy ideas, try to solve this problem, and try to use this one to do the error correction. Now, the whole theory is regarding this one, okay? So, and we also can use this type model for the encryption and decryption, okay? And also for all kinds of the communications. So that's why people call him the father of the information age, okay? Now, there's a problem for digital computer nowadays, because from the Moore's law, we know here you can see a logarithmic graph showing the timeline of how transistor counts in microchips are almost doubling every 2 years from 1970 to 2020 Moore's law. So which means the transistor size is down to the microscopic level, okay? So it's no more macroscopic. So in other words, we are going to see something like quantum effect here. Now, in 1982, Richard Feynman, okay, he proposed the ideas, a new idea for the computing. Now you can see he said that nature isn't classical, okay, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy, okay? Now, actually, a quantum computer can simulate any physical process in nature efficiently. So in this case, okay, we can use it to solve some problem, like a very difficult problem, like to find the some physics to find out some physical phenomena like the dark matter, like dark energy, and also we can help us to design some drug to do some drug design, like drug design simulation, like the COVID-19 vaccines. Okay, so this is very good for the hard problem. But problem is, some kinds of problem we cannot use the quantum computer to solve, like the NP-complete problem. For example, the star market prediction, okay, or some the optimization problem. We still cannot use the quantum computer to solve those kind of problem. But your problem is the regarding the nature, like physics, chemistry, or something else. Okay, you can use a quantum computer to solve the problem easily. Okay, so Schwartz, he developed this one, the quantum factoring algorithm. Okay, now Peter Shor in 1994, he tried to do one thing is using the quantum computing algorithm to solve a very large composite number. Now, and try to find its the prime factors. And actually, this problem is very, very difficult for digital computers. Even I don't think they can solve this problem with the digital computers. Okay, but it's very easy. Okay, for quantum computer to solve it. Okay, later on we'll see why I can do it this way. Okay, now in other words, if we can easily to do the prime factoring for the very large numbers, which means it's very easy to crack the private keys in cryptography. Okay. In other words, it's no more privacy. Okay. So quantum computing is about scaling. What does it mean, scaling? Okay. Peter Shor put it this way: the boundary between hard and easy seems to be different in a quantum world than in a classical world. Okay. What does this mean? Because we try to solve some problem, okay, like previously we just say to do the factoring, okay, the prime factoring for the largest number. But this is easy part for the quantum computer. But some problem, okay, for the quantum computer still very difficult, okay. And like MP previous said we mentioned the MP complete problem. Okay, so but the thing is, the quantum world is microscopic. Okay, so we try to use some physical phenomenon in the quantum world. Try to use those features or properties to solve the problem. Okay. But in the classical world, which means we are using the digital computers, okay, it's macroscopic, okay. So from these two different viewpoints, we can see it's really about scaling, okay. So how to solve a problem? Easy in a natural way. Probably we just use a quantum computer, okay. Now here we define the qubit. We know the bit as a binary digit. Actually, this word is coined by Claude Shannon, okay, and it's only 0 or 1. So either way, it's 0 or 1. Either way, it's 0 or 1. Okay, so like the previously, we see the digital signal. Like this one, we have the high voltage represent the 1 and low voltage for the 0. Now qubit 0 and 1 exist simultaneously, which means we can have 0 and 1 at the same time. Okay. Now this is this one we call it coherent superposition. Okay. Now that's the feature for the quantum in the quantum physics. Okay, so physically we can have the different ways to build set up the qubit. Now the first one here, we can use electromagnetic field. Okay, so you can have the rotation, okay, for the electron to determine how it what's the 0 or 1 of the photon polarization. So you use light. Okay, simply use light and you to oscillate, and the photon you can determine 0 and 1. And third one is here we we can see an internal state in an atom. Okay, so you have different way to solve it to create this qubit. Okay, actually you can have the different like a superconductor. We also can have the we also can build the qubit. Okay. Now mathematically, qubit is a vector in a 2D complex Hilbert space. Now this one here, actually we have the two state here. Okay, one is state 0 and one is state 1. Okay, now the alpha and the beta here are the complex numbers. So which means we have the two states, okay, at the same exist at the same time. We know the Hilbert space. Hilbert space, which means we have the properties of the inner product. Okay, so we do the inner product. Okay, we can define this Bloch sphere. Okay, and this one here, the 0 and 1, that's the south pole and the north pole on this sphere. So since alpha squared plus beta squared is equal to 1, so which means all the information is on the sphere surface. Okay, so it never get inside. Okay, so and then how to define the alpha and the beta? We just simply from the geometry we can define alpha equals cosine 1/2 of the theta. That's this theta, this degree here, and this angle here. Beta is the e to I v times sine 1/2 of theta. Okay, so it's just like the projection. Okay. In the two different coordinates. Actually, this two coordinates system is a orthogonal system. And actually, you have to have the orthogonal system in order to get the correct answer. Okay. Now, so we use this property to solve the problem mathematically to define the qubit. Okay. Okay, here I would like to talk about some fundamental concepts of the quantum theory. We know from the quantum theory here, indeterministic, which means that the basic ideas, those ideas from the quantum, basically the features. Okay, now okay, we can see the okay, so indeterministic, which means it's not the we can have the randomness here. So that's the actually it's an intrinsic property for the quantum phenomenon. Okay. And actually, this one here, as the we try to find out the one thing is the everything we can predict is based on the probabilities. Okay, so that's the basic idea behind the deterministic. Okay, the second thing is the interference. Interference means we have the wave and also particle, the two different the properties. Okay, so this is also the special one for the quantum phenomenon. Uncertainty is the sometimes we say in the classical information theory, the uncertainty means we don't have the knowledge, so we try to to measure something, okay, or do some prediction. But actually, in quantum theory, uncertainty is intrinsic, which means you cannot predict it. It's not pseudo random. Okay, it's real random generator. Okay, so uncertainty here is the very It's a very feature for the quantum physics. Okay. Now the superposition, like the one we said, we just mentioned before, the 0 and 1, we have coherent, the superposition, right? And that one here is the way we try to solve the problem. Because you try to solve the problem, and it's not just like 0 or 1. It's the 0 and the 1 at the same time exist. Okay, so that's the way we try to solve the problem. And the last one here, entanglement. Now this is what the primary the phenomenon we use to build up the quantum computer. Okay, now let's take a look here. Now the quantum computer with many qubits. Now suppose we have this one here, and that's just one qubit. We have the many qubits to have this one to build up a quantum computer. Now what's the problem, or how hard it is to to build this quantum computer? Okay. First one, these qubits are the information carriers, which means we have to ask these qubits to interact with each other. Okay, they shall interact strongly with one another. Okay, but the problem is how to do it. Now suppose we want to ask or control these qubits to interact with one another, which means we are going to change or alter the qubit states inside. Now, in that case, we won't get the correct result, or we just build up the errors. Okay. Now, if we just isolate this part, okay, then we cannot control all the algorithm or all the process computing inside. So that's not another problem here. So then, how to do this? How to put all those qubits together in order to perform the computing here? Now, one way you can do here, because we have the problem, the coherence here, decoherence here. Decoherence here, it's a phenomenon. Okay, like for example, today if I like to ask the computer to process something, or to ask the computer to do some algorithm computation, then the problem is how to ask those qubits to run the algorithm. Okay, you have to send the signal inside. Then you have to send something inside. Then you change all the states of the qubits. Okay, so that's the problem here. And sometimes, if you cannot isolate the system well, then you are going to have some leakage, which means the information leakage. In that case, you also change the qubit states inside. Okay, so this kind of problem we call it decoherence. Okay, now decoherence alters the qubit states that will cause the errors. Okay, so in other words, we need some way to correct these errors. Now this one here we call quantum error correction. It's pretty much like the previous one in Shannon's theory. Okay, since Shannon has no idea how this one been changed. So I mean the signal or the binary data be changed. So he developed one thing, that's the entropy, okay, to measure the uncertainty, okay, in order to do the error correction, okay. Now, it's different here. We have the quantum computing, but the way to do the error correction is quite different from the classical one, the classical information here. Okay, so we come back to this quantum computing problem. Now, how to solve this problem? Okay, we need to develop a new theory for the information theory. That's what we call the quantum information theory to solve the problem. Okay, now it's the so it's come back to the mathematical model. Okay, so when you try to solve this problem, one thing. The other thing you try to you need to solve at the same time. That is how to make this qubits interact strongly. Okay, which means you can do the computation. One way we're using for this problem, we are using the entanglement. Okay, which means we make those qubits entangled. We have the entangled qubits, which means this one will resolve the decoherence problem. Okay, so what's the entanglement? Okay, how it works? Well, actually, think about this. Suppose we have the several qubits. Each one carry the information inside. Okay. Just like a book, okay, you have the different pages here, okay. Now, suppose we want to get some information out. We can read every page. That's the way in macroscopic, okay. But in microscopic, okay, you cannot do this, okay, because you are going to change the information inside the qubit. So all you can do is try to entangle all these qubits together, which means you just not read one page to get information. You have to read a whole book to get information. Okay, so if you can make this entanglement of all these qubits, then which means when environment try to send some signal or information inside, it won't change the qubit states inside because everything is entangled. Okay. Now, same thing here. The leakage won't change the qubits inside. So that's the way how the quantum computing do. Okay. Then we can do the those difficult problems, to solve those difficult problems using quantum computing. Okay, now so this is the way to solve the problem, and the problem is when we try to solve this kind of problem. Previously, I mentioned one thing as when we try to solve this kind of problem, we only can solve those kind of problem, has some natural phenomena or something we cannot solve in digital computers. Okay, because you try to do some simulation. Now, this simulation can relate to some natures. In our natures, for example, like we try to model our brain, okay, like neural networks, okay. If you try to model your brain, and the way you can do, you have to do it, naturally. It doesn't like the previously we use the neural networks, artificial neural network. You're simply using the linear model, try to solve the problem. Okay, instead you have to using quantum computer to simulate the real the brain's structure or the neural networks. Okay, to solve the problem. Okay, and that's why we have to use quantum computer to get involved to solve those difficult problems. Okay, but for those digital computers, we still can use it to do some simulation. We also can use it to build up the prediction model. Okay, the thing is, the beauty is when you use a quantum computer, the computing time is very, very short. Okay, for example, you can simply just use a few seconds to calculate, to get a result for a large numbers, the prime factoring. Okay, but when you use the digital computers, even use your parallel processing, it may take a long time to finish it. Okay, so that's why we need to build up the quantum computer in order to solve some problems the digital computer cannot do it. Okay. Okay, so all the things here we try to explain because everything just still ongoing. Okay, so sometimes we need to take time.
So I think we're experiencing some technical difficulties, so if you guys can just stay on the line for a little bit, and we'll wait for Hu Dongxing's connection to be restored. I'm contacting him right now.
Hi, so the lost connection.
Oh yeah, we can hear you now.
So how long ago?
About 3 to 5 minutes ago.
3 to 5 here?
Yeah, roughly.
Okay. Quantum computer. Actually, we have the we can build up the quantum computer with many qubits. Okay, to have this multi-qubit system here.
The screen sharing as well for the
oh,
for the PowerPoint.
Sorry.
Thank you.
Will that be okay?
Awesome. So see it now.
Okay, this one here. Decoherence, right?
Yes.
Okay. Okay, we come back to this one here. Actually, decoherence, because if we just let the quantum computers to solve the problem inside the system, okay, there's no problem because you won't have the interaction with the environment. But when you have the interaction with the environment, you will have this one so-called the decoherence problem here. Because when you try to control the qubits inside, or you want to ask those qubits to run some algorithm, then you will change the information, okay? Change the state of the qubits inside the quantum computers. And sometimes, because isolation is not good enough, it's very hard. So you also can have some leakage coming out. That also can change the qubits states within the quantum computers. So, which means decoherence alters the qubit states. That means causing errors. Now, how to solve the problem here? We have to using some error correction method to solve it. And this one here, we call it quantum error correction. And previously, in Shannon's theory, we know Shannon used entropy to define, to measure or define the uncertainty of those due to the errors. Okay, so how to do those correction for error corrections? Now, but the quantum, we have to do it quantum way. Okay, it's quite different from the classical information theory. Okay, because everything you see here is superposition. Okay, so you have 0 and 1 at the same time. So you try to do it the quantum error correction way. Then, and that's the quantum information theory comes in. Okay, and everything's still, I think it's still undergoing. Okay, so here, we need to talk about, so I leave it right here. And then I need to talk about one thing here is, since if you can, isolate all the qubits inside, the next thing is how to make those qubits work together. Specifically, okay, make them, interact strongly with one another. The way you can do here is try to make all the qubits, entangled. Okay, so inside, when you can make those qubits entangled, which means you do one thing here. Okay, you make everything and all things, just like in reading a book. Okay, every time you try to read a page from the book, okay, you can get information. But when you put those pages entangled, which means you cannot get the information out of one single page. You have to read whole book, okay, in order to get the information. And that's the entanglement trying to solve the problem, okay? So we try to make all the qubits entangled, okay? So inside, maybe you have some quantum channel, okay, to solve this kind of problem, to make an interaction. But from the outside, the environment, okay, since environment is decoherence, so which means environment won't see the entangled, the qubit states inside, okay? So suppose you try to control the things, you send in the information, or you try to run some algorithms, it won't alter the qubit states inside, okay? In that case, we can run the quantum computers, okay, in order to resolve the decoherence problem, okay? Okay, this kind of problem here, this kind of way we try to solve the problem, and we can solve some very difficult problem here, because we try to use quantum physics properties or features, try to use this kind of phenomena to solve the problem. And it's different from the binary system, the digital computer, the one try to solve the problem. For example, if we want to modeling human brains, okay, we try to do some neural network, okay. Previously, we in the artificial neural network, we try to use the simple model like linear models, right? We can do some parallel processing in order to solve the problem, to get something, to get some result out of the artificial neural network. But the thing is, it's not a real way to solve the problem in our brain. So if you try to model or simulate the brain's work, okay, you have to use quantum computer, okay, and that's easy. I mean, easy means it solves it very, very fast, very efficiently, okay. And like this kind of problem, we can use quantum computer to solve it. Okay, so a quantum computer can simulate any physical process in nature very efficiently. Like we try to solve some problem for dark matter, for black holes, okay? And even we can solve the problem for COVID-19 vaccines design, so to do the simulation, okay? However, for some problems, quantum computers cannot perform the computation well, specifically for NP-complete problems, okay? We try to do some optimization problems or stock prediction. Those kind of problems are very, very difficult for quantum computer, okay? But if you try to solve the problem like dark matter, COVID-19, you probably won't use few seconds, you can get all the results out because you have the qubits here. That's superposition. You can get all the results out, you know, at once. So quantum computing solves the hard problem in a natural way. Okay, we tried to solve the problem previously using the digital computer, but in the future, okay, we try to solve a problem specifically like a physics problem, like in chemistry, okay, or even in medical health, we are going to use quantum computer, okay. So I think that's very promising, okay. Here, a few more words for the young people here. Just from the future viewpoint, okay, where do you see yourself in 10 years, okay? Because next 10 years, Okay, Google, for example, like Google built up a Google the quantum AI center, right? So that's the opportunity, and that's the future. Okay, for young people, I think if you like, I think this is a very, very good opportunity for you to get into the quantum computing or even the quantum AI, and I think that will be you are going to have a bright future. Okay, at least 10 years. Okay, so I think that's end my talk today. Thank you for your listening and patience, because I have already worked for 20 hours, and so I'm very tired here. So I'm sorry. Any question?
Thank you, Professor. That was a very interesting presentation. And as you were mentioning about Google is now doing has a quantum AI laboratory, and now NASA as well. They have what's called
they work together.
Yeah, SQAI, the quantum AI laboratory that they opened up. Actually, it's been open for many years now, as far as I have been, as far as my research has gone. So it's very interesting topics here. And thank you for joining us.
Sure.
And
any question here?
Hello, can you hear me?
Sure, go ahead.
Yep. So I want to ask that from your perspective, what is the potential opportunity for Taiwan? Like, what is the possible application for the quantum AI that can benefit Taiwan, or someone in Taiwan can have some developments on it?
Just take a look at this, COVID-19, right? We need vaccines, right? We need some medicine to cure the disease. So I think that in the future, if you try to, it's because it's very hard to solve the problem like the pure. I think that just the pure science for pure science, because you cannot survive in that way, because I'm an engineer. Okay, so from this point of view, I think that you have to do some applications. Okay, not just do some research. Basic research is fine. Okay, but most likely for Taiwan, since you mentioned Taiwan, I think the most likely you have to do some applications. Specifically, this time, the almost 2 years here, we have we are suffering the COVID-19 disease, and nowadays the things are even worse. So how to solve that? And even we can help people, in Taiwan or even everywhere. So I think that quantum AI can get into it, and we can solve the problem and get some benefits, and even make some money. We don't just always we don't need to always depend on some 护国神山, right? Okay, so that's the problem. I think the quantum AI is pretty promising. Okay, but the first thing, you have to have the quantum computer first, right? Coming out. Okay.
Yeah, thanks. I agree with that.
Sure. Any question? Because this field is still quite new. Something still under developing. So we cannot talk too much about the latest things, because we don't know the latest development. All we need to know is some basic ideas, how it works, okay, and what we are going to do to learn it, and eventually we can take some benefits, or some we can gain something, okay, out of this research, okay.
Let me reemphasize: we are the first conference in the entire world to be talking about quantum AI. We are the first in the world. There is a quantum machine learning academic journal by Springer, which is also the people that create Nature.
That's true.
But we are the first academic conference in the world with QAI, quantum AI. So we're talking about a very new subject here.
Yeah.
You're mentioning about Google quantum AI, and then also IBM as well. The next in our 529 session in next Saturday, we'll also be having NTU IBMQ director Zhang Qingre to discuss, like for example, fintech. Like you're mentioning about medical applications as well. And then Professor Liao also did a little bit of research into the medical applications. And the NTU IBMQ director did some research in the applications to fintech. So a lot of different potential applications. And right now, it's sort of like the parallel to it in terms of pure AI would be like artificial narrow intelligence. Well, this is artificial. Well, this is narrow quantum. This is narrow quantum AI. Once we're able to get to general quantum AI, that's what everyone's hoping for. That's the future. So.
Okay, good. Okay, good. So I probably will do this presentation again, and I will record it and put it on YouTube later on. And so if you like, you can get on the YouTube channels to review it again. Okay, I think I would just spend some time just 再看一看 ，OK， 再 review some articles, and because it's too new and to cover all the things inside, and I think I try my best, okay, because they're too busy to do so, and so I hope NTU and even the NCU can make some progress in quantum computing and also quantum AI in the future. Okay. Okay. Thank you for having me here. Okay. Thank you, Sas. Thank you. Thank you, everyone. Okay.
Thank you for joining us.
Sure.
Glad to host the session with everyone. And in terms of right now, we're going to have a little bit of maybe a panel discussion, but also we want to discuss the prizes. So Wayne, if you are online, if you can hear me, I'm not sure if he's here. Here, I'll contact him really quickly on Facebook. Just bear with me for a moment. All right. 1 second. So I'm gonna quickly record my screen. It allows for me to. Okay, can everyone see my screen?
Yes.
Okay, cool. So I'm gonna give, so kind of how the rest of this meeting today is gonna be structured is, I'm gonna give a brief introduction to the sponsors of this event for 520 today, as well as 529 next Saturday, which is starting again at the same time, 4 o'clock. We have our link posted in AI Club in the 就是那个活动的链接就在那个我们的 AI 室的分专上。And so essentially, we have Microsoft who's sponsoring us for this event, as well as Reliance Biosciences. And Reliance Biosciences' CEO is Andrew Huensel. And they're a 新创公司. They're a startup that's based in Taipei, and they have their office now. And I worked with them in 2019 for 5 or 6 months, and they're doing a lot of great research in Alzheimer's disease and early prediction of it. And they have, so there's something called Ymiti in Chinese. It's exosomes. Exosomes are it's a structure in the blood that is in cells that allows for us to be able to do certain types of diagnosis at a more quick rate. And they also have done biomedical AI research, and they're one of our silver sponsors. And we also have apbcd.org is their website. APAC Blockchain Development Association. Is someone raising their hand? Okay, yeah, so at the very end of this presentation, we'll have Wayne to announce the prizes for people that are on the line. So make sure to stay on the line if you're interested in winning a prize. And so this is our website here, and as you can see, we have the poster that we just recently designed. We also have all kinds of all kinds of different projects we've been working on, like Xiedong, Xie Mingfeng, we call him Xiedong. He's the PhD I was mentioning, and we work together on agricultural blockchain, all kinds of different projects with Professor Liao, and they've been sponsoring us. And it's an organization of numerous professors, and they are at the forefront of blockchain research. So make sure to check out their website, appbcd.org. And we also have smart contract research forum. We call them SCRF, SCRF, and they're based in Palo Alto, but actually we have a whole team based around all throughout the world, even though we're based in Silicon Valley. And so kind of just going through this one more time, just for fun. Right after this, I'm going to get into a little bit more detail of SCRF. So we had Professor Hu Zhongxing, as well as Lieutenant Akujobi, as well as several, about not even half of the presenters presented yet. So we're going to have Zhang Qingrui and Hong Sihao and Professor Martin and Professor Liao and Elvis and Sean and Tenri and NGV and Tenyu Liu, Mark Chen and Professor Paganis as well. They're going to be presenting next week, so make sure to stay tuned for that. And again, we are the first conference in the entire world that is focusing on this very new topic. It is a very new topic. It's about how can we use quantum to optimize different AI algorithms. I would argue that IBM is at the very forefront in terms of this research. The very forefront in terms of well, quantum as well. And here we have smart contract research forum. Now I'm going to actually start off this by introducing the website as well. So if everyone can follow along with me, basically, oh cool, it's making subtitles. I didn't even know that Google Meet could do that. Anyways, cool functionality. Basically right here, I'm just gonna log out. And you guys can all create your new accounts on Smart Contract Research Forum. I'm just going to create a new account just for the heck of it. And just enter your emails just like anything. I'm just going to call this Gear 2 and Seth 2. And actually, no, you don't have to have any. And so I'm going to have it recommend a password for me. You guys can steal this account because this is a recorded session. So. Incorrect user, whatever. Create your account. It allows for me to create my account. Please enter your email address and enter it one more time. Toss. And this forum is new in the fact that we make research summaries in blockchain and allow for the entire world of blockchain to become more understandable, to become easier to kind of delve into the research of it. Because pre-existing kind of blockchain forums have been a little bit less technical. They don't have a lot of professional content on them. And we're a startup that was funded specifically by Chainlink. Now, Chainlink is one of the biggest blockchain companies in the entire world. And they gave us a bunch of money, a bunch of funding for doing all kinds of cool stuff in the field of blockchain research and working with blockchain clubs like at Cornell and at MIT. And they're working with us here at NTU as well. And as you can see on their forum right here, they have all kinds of cool topics. These are the main topics in blockchain research. So things like cryptography, mimashu, tooling and languages. So if you, like for example, if you have some sort of benchmarking tool, for example, Blockbench or something, that would probably fall under tooling. Governance and coordination. So for example, electing of leaders, scaling and making larger blockchains and increasing throughput and stuff like that. Consensus algorithms, proof of work, proof of concepts, proof of memory, proof of storage, and then we have metadata as well as all kinds of different stuff. And essentially, most of the content falls under the category of research summaries or discussion posts. Now, we also every single month have what's called a research pulse, and this month we had research pulse issue number 13. Excuse me, every single week. And I had actually just joined Smart Contract Research Forum just a couple weeks ago. So I'm fairly new to it, and it's been a lot of fun. And so one of the nice things about this working environment is you get to determine how many hours you want to work. The salary is $25 per hour. American 25 USD, so it's pretty high salary. And you get to determine when you want to work, what you want to work on, as long as you give a proposal, and the proposal gets approved by the reviewing in the reviewing process. And I would highly recommend you guys check out the website right now. So we're building a bridge between academia and engineering. So this would be 产学合作. And as I was mentioning about the different categories, and so we need people to begin, we need people not only of blockchain backgrounds, but people of fintech backgrounds, people of all kinds of, not only engineering backgrounds, but even if you're journalism, we have all kinds of different people on the team. Some people have a strong blockchain background, and some people are maybe they're just starting out, and that's fine too. But we need different smart people from all different kinds of backgrounds to get the conversation started. We have research, we have different discussions about all kinds of different topics. And so to start off, after you've created your account, the first step is to connect. And so you could either on Discord, our Discord server, I'll be providing that, or on our forum. In terms of on our forum right here, maybe you could find one of our posts, like for this recent post here, and you could leave a comment here. And this is how you guys could all start off, if you're interested in joining us. And you could just talk about what time zone you're in, and for different posts, just talk about like what you found interesting in their post, or maybe some suggestions and whatnot. And we're all, it's a very open forum, and it's a lot of fun. And all the time that you spend on this forum and on building it is going to be compensated. And we prefer to pay in Link, but because our parent company is Chainlink, but actually we can pay in all kinds of different cryptocurrencies. There's Bitcoin or Ethereum or you name it. We can, for the most part, just about any cryptocurrency works. And it's also, if you're not allowed to accept income right now, then that's fine too. Like, for example, if you're participating in an academic conference, we could fund the travel for that, or we could donate to a cause of your choice. And so if there are any questions so far, you're welcome to leave a comment here, or actually I'll give my contact information for anyone interested in joining. And there's also James at smartcontractresearch.org, based in Palo Alto. So I'm just going to say leave your resume or LinkedIn, or Angie's List, etc. I would say attach your resume and send it in an email to James. And you could also explain, what type of blockchain technology that you might be interested in, or what sparked your interest in blockchain, all kinds of different stuff. What's your favorite cryptocurrency? Or maybe you saw some news about Bitcoin recently, or about Dogecoin, and that kind of sparked your interest in blockchain. You don't have to be an expert in it, but you do have to be willing to learn. So, and essentially, we have. I'll get in a little bit into the technicalities, but not too much. It's just we have a public drive, and we use that to Google Drive just to share kind of a lot of the content. And as I was mentioning earlier in the conference, we also use a public GitHub repository, and that's located directly at github.com/orgs/smartcontractresearchforum. And I'm just going to send this this organization link to you guys. And so this is a great work opportunity. And actually, Sean is going to be giving a presentation on quantum blockchain next week. And I would argue that in terms of this new and growing field, quantum AI, it's not just about quantum AI. It's also about the quantum, it's also about AI, and it's not just pure quantum or pure AI. Being able to understand and study different interdisciplinary quantum or interdisciplinary AI fields. For example, it could be like quantum blockchain. It could be computer vision with VR, for example. These types of things can give us ideas as to how to build these new domains and how to bring knowledge into these new domains. So it can bring a lot of different interesting insight. We don't require absolutely require that it has to be specifically emerging quantum AI. It can be just quantum, it can be just AI, it could be interdisciplinary quantum, it could be interdisciplinary AI, and it could be blockchain AI, all kinds of different cool stuff. And that's how we're starting. And so kind of when we're proposing different topics here, we have a specific selection criteria, and that is that we want to have something that's conceptually easy enough to understand that a lot of experts in the field are able to understand it, or just even having a general audience able to understand it is quite a good thing. When it's applicable to a wide area, for example, something like if it's a summary of maybe how to find Bitcoin tracing, for example, how to trace, for example, malicious nodes on Bitcoin network, on Bitcoin's peer-to-peer network. That would have a broad applicability to the field. Is it new? Is it new enough? And is it timely enough? So, for example, are we going to be looking at papers from 2011? Maybe on occasion, but for the most part, we're going to be looking at the newest stuff. We want to stay at the forefront of the blockchain field. Has been recently discussed on the media. Our industry participants currently discussing this topic. All of these kind of four features would allow for it to be give it a broad debate quality to it, and allow for us to have relevant, strong material for our forum. And so again, you can kind of start off in several different ways. So if you're looking for a topic to kind of start researching on, because before you go for an interview, I would highly recommend you guys to go find a topic that you're interested in. It could be either on the Research Pulse, which is on our website, or it could be on the Icebox, which is on our GitHub. You guys could check this out. So we have peer review. So this is kind of like how we start off, is with an idea proposal. And then once that idea gets kind of past, it's like, okay, this idea might be acceptable, then it goes into the drafting stage. Then we get peer review, then we get final content review, then we get editorial review, and then we finally are able to, through numerous steps, get to publish it. Now, there's also a possibility that it goes into the Icebox. And the Icebox is essentially the ideas that we've suggested, but that we haven't implemented yet, or maybe for the time being we're not going to implement. And maybe you have a different approach, or maybe you have a different suggestion for how we should kind of discuss these different topics. And that's totally cool. So maybe you could find, like, for example, if I want to talk about the Byzantine generals problem, because that's one of the biggest topics, is Byzantine fault tolerance, BFT. That's one of the biggest and most prominent topics when it comes to blockchain. And like maybe having a different proposal for how you could do research analysis on that. Or maybe you have a paper that you've read, an academic paper that you've read recently, and you want to make an academic, a summary on that. And that's totally cool. And so right now we have a team in Taiwan. We have a team in Europe, and we have a team in America. And I believe that one guy in America is working in the East Coast, and the rest are on the West Coast. And so we have all different time zones. So the sun never sets on Scurf, just as a joke, because 24 hours a day someone's doing work with Scurf. So because we have teams from all over the world. Yeah. Anyways, if you are interested, and you could contact either me, or you could contact James, or you could make a post on the forum first. And we're welcoming people of all kinds of different backgrounds. And so that's Scurf is our major sponsor for this event. And so that kind of concludes it for my introduction to our sponsors for this event. Please stay tuned for next week's event. And now I'm going to hand it off to Wayne for discussing the prizes for anyone that's online currently. So, Wayne, if you're online.
喂
Hello.
听得到吗？
听得到。
OK， 那我们现在就直接来抽了。OK， 那就截止我分享一下画面。OK， 看得到吗？
看得到。
OK， 然后现在就截止哦。我们总共现在有29个，很少，所以抽奖蛮高的。所以大概看一下，我们有大概27个人都是男的，是男女比。好，所以有蛮多是17个人是实学生，这次抽奖的人，然后我们就直接来抽啦。这次介绍一下我们的那个的奖品，因为原本也说4个，但是人太少了，我们合并成3个，总共是1000元现金一个人，然后500元现金2个人，然后目前的话人数的话就是29个这里面，那我就现在来复制，然后现在就抽奖。好，那都输入完之后，有要先试抽吗？试抽的话就是没有中奖的话不要高兴，因为还会再抽一次，试抽一次好了，代表说我们没有作假。好，试抽一次看看是不是。好，恭喜Anthem Sign。哦，对，等一下的规则就是我会再叫人，抽完之后叫人他要在现场才有，没有的话就是我们再抽一次。啊，那如果叫3次没有的话，就是放弃了这样。好，那这个不要难过，也许等一下还会是你这样，都不一定。好，那就是要现在现场哦。好，那我们现在就正式来抽。好，那正式抽奖了，当然，好，等一下就再抽一个，这个是我就放弃，等一下再抽一个。好，先问一下林静佳在现场吗？是的话你就开麦克风跟大家讲一下。林静佳，
我在现场。
你在现场，好，恭喜你获得500块现金，然后到时候私信我们粉专就可以获得了这样。好，然后第2名是1000元的幸运得主邵轩磊，在现场吗？邵轩磊是台师大的 H 开头的，有在现场吗？1次。邵轩磊有在现场吗？不在。2次。邵轩磊有在现场吗？3次。好，那就没有了，那我们就再抽一次1000元的。还有吗？还有机会吗？有人知道他在现场吗？还是去上厕所？没有就好，放弃了。那就等一下再抽一个500元现金跟1000元现金。好，因为最后一个这是我，所以就算了。好，那就是500元跟1000元现金，那就现场直接来抽。那要在现场哦，刚刚像邵先生就太可怜了，就没有的话就放弃了。好，那再走我就直接抽了，就不试抽了。好，噔。好，梁家园在现场吗？梁家园有在现场吗？1次。举手了，他举手了，好，看到了。好，那就等一下一样，到时候私信本专，然后看领取的方式这样。另外一位是林敏瑞嘛，你们念错，电机系的同学在现场吗？电机系，林敏瑞，我们念错，林敏瑞嘛，林敏瑞在现场吗？电机系的同学，1次，林敏瑞2次，林敏瑞3次。好，那就拜拜，就再抽一个好了。好，那就是只剩下1000元现金，那就是再抽一次。敏锐有在现场吗？没有哦。好，那就再抽一次。好，直接抽了。噔。又是他，邵轩磊。刚刚有说过吗？邵轩磊。中2次， 邵宣伟2次，邵宣伟3次，那就再抽一次。好，再抽，再抽一次。硬要的有在现场吗？像北科大的硬要的，北科大资工系硬要的有在现场吗？北科大硬要的2次，北科大硬要的3次没有。好，再抽一次好了。杨宗儒竹科时钟的有在现场吗？杨宗儒竹科时钟的，杨宗儒2次，竹科时钟杨宗儒3次有在现场吗？杨宗儒3次，哇，没有在现场。好，那如果在最后再抽一次好了，不然整个晚上我们都来抽奖，就是抽完最后一次，如果没有的话，就是我们再看联谊看店名要怎么样抽出来这样。好，那就最后一次抽人，好，最后一次，希望他可以在现场，就不用再抽一次这样。好，噔，这个重复中奖我们就，林敏瑞刚刚有，敏瑞好像重复了对不对？重复了嘛 ？SS 你看你要怎么样？现在重复然后一直都不在。好，重复我们就不算，我们再抽一次好了。重复刚刚应该是没有，也没有。林敏瑞还在吗？这中奖几率很高有吗？没有，那就再抽一次，最后一次，不要重复，你就最后一次。噔，周有成，工科海洋有吗？周有成没有就我们就再演绎看怎么样，不然。周有成2次有在吗？周佑成有在吗？2次。周佑成3次。好，没有。SS 你要不要看一下还要怎么样？我们就之后再。
万一没有抽中你，干脆把它移除掉就好了嘛。
哦，把它移除掉吧。好。
对啊，不然你一直重复不是吗？
好，那就把刚刚的移除掉。我先把我移除掉，然后刚刚敏锐移除掉，小轩磊也移除掉。好，那就再抽一次了，那就希望他会在场。好，噔，梁家园，是不是刚刚抽过？有吗？刚刚梁家园有在现场吗？梁家园有在现场吗？有吗？梁家园2次。OK， 好，那太好了，就抽完了。那你等一下到时候也是欢迎私讯一下本站。那我们今天抽奖就到这边这样，恭喜3位得奖者这样，谢谢。
Okay, thanks guys for tuning in to today for SQAI Day 1, and make sure to check out our events at SQAI Day 2, which is going to be on the 29th of May, so 9 more days. And we're going to have a lot more speakers as well from a lot of different interesting backgrounds for IBM Q, for NTU, for different departments, and from physics, from computer science. Because that's what quantum AI needs, is people, especially from physics and especially from computer science because of AI. And we're looking forward to seeing you at the next event. So good night, everyone.
Bye-bye.
Thank you, Seth.
Thank you, Professor.